Hello there, and welcome to Science for Sleep, a quiet place where curiosity is allowed to slow down, where big questions are explored gently, and where learning never needs to rush anywhere. Wherever you are right now, whether the lights are already dim or the world outside is still moving, you've arrived at a moment where nothing urgent is required of you. Tonight's exploration is about something so small that it almost feels strange to talk about it at all. A place where the usual ideas of space, distance, and size begin to lose their familiar meaning. Before we go any further, take a second to notice where you're listening from. Maybe you're lying in bed, maybe you're resting on a couch, maybe you're somewhere in between sleep and waking where thoughts feel softer around the edges. What time is it where you are right now? Not the exact number, just the general feeling of it. Late evening, early morning, that quiet stretch when the world seems less demanding. It's fitting, in a way, because the topic we're easing into tonight sits right at the edge of what the universe itself can meaningfully describe. If you find this kind of slow, thoughtful science comforting, or if it helps your mind unwind after a long day, you're always welcome to support this space by liking the video or subscribing. It helps this calm corner reach others who might be looking for the same gentle pause. There's no pressure though. For now, all you need to do is listen. So let's begin, not by racing outward to distant galaxies or massive explosions, but by doing the opposite. Let's imagine shrinking. Not shrinking in a dramatic movie-style way, but carefully, step by step. Like turning down the zoom on a microscope that keeps going far beyond what it was ever designed to show. Imagine looking at the space around you, the room you're in, the air between objects. At first, everything feels continuous and smooth. Space feels like an unbroken stage where things simply exist at different locations. Now imagine zooming in. The wall becomes a surface made of tiny imperfections. Zoom further, and it becomes a collection of molecules. Go further still, and those molecules reveal atoms, mostly empty space with dense centers and electrons that don't really orbit in neat paths the way textbooks once suggested. Keep going, and even the atoms lose their solidity. You find protons and neutrons, themselves made of quarks bound together by forces that don't behave like anything in everyday life. At each step, space still seems to exist as a background. There's still distance between things, still room for movement, still a sense that you can always divide a gap into something smaller. Half the distance, then half again, then half again. Mathematics allows this forever. You can always imagine cutting space into finer and finer pieces. Physics, however, begins to hesitate. As the scale keeps shrinking, something odd starts to happen. The rules that worked so well at larger sizes no longer agree with each other. Gravity, which quietly governs the motion of planets and galaxies, starts behaving in ways that don't line up with the rules that control particles and energy. Quantum effects, which normally dominate only at tiny scales, begin to shake the structure of space itself. And eventually you arrive at a question that physicists have been circling for decades. Is there a smallest possible volume of space? Not just the smallest thing we can currently measure, but the smallest thing that can meaningfully exist. This is where the idea of the Planck volume quietly enters the conversation. The Planck volume isn't a place you could visit, or a box you could draw on a diagram and point to. It's not a location in space, and it's not an object. Instead, it's a limit, a boundary that emerges when we take the known laws of physics and ask them to work together at scales they were never meant to handle. To understand why this matters, it helps to think about how measurement works in the first place. When we say something has a size, what we really mean is that we've compared it to something else, a ruler, a wavelength of light, a tick of an atomic clock. Measurement is always relational. We probe, we bounce particles, we send signals, and we interpret how they return. At very small scales, this probing itself becomes a problem. To measure a tiny region of space, you need energy. The smaller the region you want to examine, the higher the energy required. High-energy particles have very short wavelengths, which makes them useful for resolving small distances. But energy, according to relativity, has gravity. Enough energy packed into a small enough region doesn't just reveal structure, it changes the structure. This is where the universe starts pushing back. As you attempt to probe smaller and smaller volumes, the energy required to do so becomes so intense that it distorts space itself. At some point, according to our current understanding, trying to measure a smaller region would cause that region to collapse into something like a microscopic black hole. The act of measurement destroys the thing being measured. That point, that threshold where our tools and theories stop cooperating, is closely tied to the Planck scale. The Planck length is an incredibly small distance, far smaller than an atom, smaller even than the particles that make up atomic nuclei. When you take that tiny length and imagine a cube built from it, you get what's known as the Planck volume. It represents a region of space so small that the usual ideas of geometry, distance, and continuity no longer behave in predictable ways. It's important to pause here and gently clear away a common misunderstanding. The Planck volume is not necessarily a tiny box that space is divided into like pixels on a screen. Physics doesn't currently say that space is made of little cubes stacked together. Instead, the Planck volume marks a point where our descriptions stop being reliable. Think of it like a warning label rather than a building block. When equations involving gravity, quantum mechanics, and energy densities start producing nonsensical results, infinities, or contradictions at this scale, it suggests not that reality breaks, but that our models do. The Planck volume is where the map ends, not necessarily where the territory does. Still, the implications are unsettling in a quiet, thoughtful way. If space cannot be meaningfully divided beyond a certain scale, then the smooth, continuous space we experience may be an approximation. At large scales, it works beautifully. Just like a calm lake looks smooth from a distance, even though up close it's a restless collection of moving molecules. Space, too, might be calm only when viewed from far enough away. As you shrink down toward this smallest meaningful volume, space may become irregular, fluctuating, and unstable. Some physicists describe this as a kind of quantum foam, where distances are uncertain and geometry itself flickers. Not foam like bubbles popping, but foam in the sense of constant activity, without a fixed shape. In such a regime, the idea of a straight line loses clarity. The idea of a fixed distance becomes fuzzy. Even the notion of here versus there may stop making sense in the way we expect. And yet, this isn't chaos in the everyday sense, it's not random noise. It's governed by rules we haven't fully uncovered yet, rules that would unify gravity with quantum mechanics into a single coherent framework. Whatever those rules are, they would describe what really happens when space reaches this extreme limit. For now, we're left with careful hints. One hint comes from black holes. When matter is compressed into an incredibly small volume, gravity becomes dominant, and classical descriptions of space collapse. At the center of a black hole, our equations predict a singularity, a point of infinite density and zero volume. But most physicists suspect that this infinity isn't real. It's a sign that our theories are being pushed beyond their valid range. Another hint comes from the very beginning of the universe. When we trace cosmic expansion backward in time, everything converges toward an extremely small, hot, dense state. Once again, we encounter infinities and breakdowns in description. Once again, the Planck scale appears as a boundary we cannot cross with confidence. These recurring limits suggest that the Planck volume is not an arbitrary number. It emerges independently from multiple lines of reasoning, all pointing to the same uncomfortable conclusion. There is a smallest meaningful scale, and beyond it, space as we know it may not exist in the usual sense. This doesn't mean nothing exists there. It means that existence itself may be structured differently. As you rest with this idea, notice how it feels. There's something oddly calming about the notion that even the universe has limits, that even infinity has places where it quietly says, This is as far as this language goes. We often think of science as endlessly expanding, always explaining more. But here, science is doing something gentler. It's acknowledging uncertainty. And uncertainty, when approached slowly, doesn't have to be unsettling. At human scales, space feels reliable. You can reach for a glass, walk across a room, lie down and feel the mattress beneath you. None of that depends on understanding what happens at the Planck volume. The universe is generous that way. It lets us live comfortably far above its deepest foundations. But curiosity has a way of drifting downward, asking what supports the floor beneath the floor. At larger scales, space feels dependable. You can move through it, measure it, divide it, and trust that what holds true in one place will also hold true a short distance away. If you stretch out your arm, there is space between your hand and your shoulder. If you take a step forward, you cross that space smoothly, without gaps or jumps. Even when we think scientifically, we tend to imagine space as a continuous backdrop, something that exists everywhere in between objects, filling the universe evenly and quietly. That assumption works extraordinarily well for most of what we do. It works when we build houses, when we calculate orbits, when we aim spacecraft across millions of kilometers. It even works when we zoom far down into the microscopic world of atoms and molecules. Space still seems like a smooth stage, just occupied by smaller actors. But as physics has learned again and again, what works well at one scale can quietly fail at another. The idea that space is smooth, continuous, and infinitely divisible is something we inherit from everyday experience and from classical physics. In this picture, you can always divide a distance into smaller pieces. Half a meter becomes a quarter, then an eighth, then smaller and smaller fractions without ever reaching a final indivisible unit. Mathematically, this makes perfect sense. Geometry has no problem with infinite division. Nature, however, may not share mathematics' patience. To understand why this smooth picture begins to break down, it helps to think about how we know anything about space at all. We don't perceive space directly. We infer it. We send signals through it, bounce particles across it, and observe how things move within it. Light travels through space. Objects interact across space. Forces spread through space. Every measurement of space is really a measurement of interactions. As long as those interactions behave predictably, space appears smooth. Distances add up. Straight lines stay straight. Volumes behave as expected. But when the interactions themselves become uncertain, space loses its clarity. At very small scales, quantum mechanics becomes unavoidable. Quantum mechanics tells us that particles do not have perfectly defined positions and momenta at the same time. There is always a built-in uncertainty. This isn't due to bad instruments or sloppy technique. It's a fundamental feature of how nature works. Normally, this uncertainty affects particles moving through space, not space itself. The stage stays firm even if the actors behave strangely. But when we push closer to the smallest meaningful scales, that separation begins to blur. Quantum uncertainty starts to infect geometry. Imagine trying to mark a precise point in space. To do that, you need a reference, usually something like a particle or a field. But the more precisely you try to localize that particle, the more uncertain its energy becomes. High energy concentrated in a small region doesn't just sit there politely. According to general relativity, energy curves space. So now we have a problem. To define space precisely, we need energy. But adding energy changes space. At small enough scales, the act of defining geometry disrupts geometry. This is where smoothness begins to falter. Instead of a calm, well-behaved fabric, space starts to behave more like a restless surface. Not a surface you could touch, but one whose properties fluctuate. Distances are no longer sharply defined. Volumes do not sit still. The idea of a perfectly flat region becomes increasingly questionable. Physicists sometimes describe this regime using the phrase quantum foam. The word foam can be misleading, because it suggests bubbles popping and collapsing in a visual sense. What's really meant is constant fluctuation. At extremely small scales, space may be seething with tiny distortions, constantly forming and dissolving. These distortions aren't happening in time the way waves ripple across water. Time itself is entangled in the process. The fluctuations are part of the structure, not events occurring within a stable background. In this picture, asking for a perfectly smooth distance becomes like asking for the exact position of a wave on a stormy ocean. The surface exists, but its fine details refuse to stay still. One way to see how radical this is to compare it to something familiar. Consider temperature. At a large scale, temperature feels smooth. A room can be 20 degrees Celsius throughout, but zoom in far enough and temperature stops being meaningful. Individual molecules don't have temperature. Temperature emerges only when you average over many particles. Space may work the same way. At large scales, it behaves smoothly. At extremely small scales, the concept itself may stop applying. There may be no such thing as a sharply defined distance in the way we imagine it. Smooth space could be an emergent phenomenon, something that only appears when you look from far enough away. This idea challenges a deeply ingrained intuition. We tend to think of space as something fundamental, something that simply exists. But physics increasingly suggests that space might be more like a collective behavior, arising from deeper structures we don't yet fully understand. This is unsettling, but not in a dramatic way. More in a quiet, philosophical sense. If space isn't smooth all the way down, then the universe doesn't have an infinitely fine grain. There is a scale where questions like exactly where lose their sharpness, not because of ignorance, but because the question itself no longer fits the structure of reality. At that point, geometry becomes probabilistic. Distances are described by ranges rather than precise values. Volumes fluctuate. Straight lines lose their privilege. Importantly, this doesn't mean that space breaks into jagged chunks like shattered glass. The breakdown of smoothness doesn't imply ugliness or disorder, it implies limitation. It means that smoothness is an approximation that works astonishingly well above a certain scale and quietly fails below it. This shift has profound consequences. Many of the tools physicists rely on assume smooth space. Calculus, for example, depends on continuity. You take derivatives by imagining infinitesimally small changes. You integrate by adding up infinitely thin slices. If space itself cannot be divided indefinitely, then these tools must eventually give way to something else. That something else is still being developed. Different approaches to quantum gravity, the still unfinished framework meant to unite general relativity and quantum mechanics, propose different answers. Some suggest that space has a discrete structure, built from fundamental units that cannot be subdivided. Others suggest that space is not fundamental at all, but emerges from relationships between more basic entities. In either case, smoothness is no longer guaranteed. One particularly interesting consequence of this is that the idea of a perfectly empty region of space may not exist. Even in the absence of matter and energy, the smallest volumes of space would still fluctuate due to quantum effects. Absolute emptiness, perfectly flat and still, may be an illusion. This gives space a subtle texture, not something you could feel or see, but something that becomes relevant when you push physics to its limits. It also reframes the question of what space is made of. In everyday language, we don't think of space as being made of anything, it's just there. But if smoothness breaks down, then space may have an underlying structure, even if it doesn't resemble matter or particles. That structure could be mathematical, it could be relational, it could be something entirely unfamiliar. What we do know is that when we push our theories toward the smallest scales, smooth space stops cooperating. Equations that assume continuity produce infinities. Predictions lose meaning. Results depend sensitively on assumptions that no longer hold. This is not a failure of physics, it's a signal. It's the universe telling us that we've reached the edge of a useful description. And edges, when approached slowly, are informative places. There's something almost reassuring about this. It means the universe isn't obligated to conform to our intuitions, even our most refined mathematical ones. It has its own structure, and our understanding improves by recognizing where our pictures stop working. As space stops being smooth, it doesn't disappear. It becomes ambiguous. It resists being pinned down. It invites new ways of thinking, and that invitation leads naturally to a deeper question. If space cannot be divided forever, how do we even talk about shrinking further? What happens when we keep zooming in, not visually, but conceptually, trying to imagine smaller and smaller regions despite the breakdown of smoothness? Alright, let's take the gentle idea we've been circling and make it more concrete. Not by snapping into formulas or racing toward conclusions, but by doing something surprisingly powerful, something humans do well without noticing. Let's shrink things in our minds, carefully and patiently, as if we're turning a dial one notch at a time. There's a reason this works. We can't physically hold the smallest scales in our hands, and we can't travel there with a microscope the way we travel to bacteria or cells. But we can build a chain of understanding where each step is small enough to feel familiar, and each new step borrows its sense from the one before it. That's how most of physics is learned, really. Not by leaping straight into the deepest unknown, but by making a series of reasonable moves until you arrive somewhere that would have seemed impossible at the start. So imagine for a moment that you have a way to shrink your point of view without shrinking you. You stay comfortable and safe, you're breathing steady, your thoughts unhurried, but the scale you're looking at changes. You can still see clearly, still think clearly, but what counts as small keeps shifting. Start with something very ordinary. Picture a room. It could be the room you're in, or any room you know well. The distance from one wall to the other might be a few meters. The air in between looks empty, but it isn't. It's full of molecules, and those molecules are moving, colliding, carrying heat, carrying sound, carrying smell. Even when nothing seems to be happening, the space is busy. Now take one step down in scale. Instead of meters, think in centimeters. The room is still the room. Nothing dramatic changes. You can still describe distances with a ruler, and the idea of smooth space holds perfectly. You can pick any point between 2 points, and there will always be another point between it and its neighbour. Space seems like an uninterrupted continuum. Take another step down, millimeters, still smooth. The surface of a table starts to show texture, tiny scratches, dust particles, but space itself still feels like a continuous background. You can still draw a straight line, and it still behaves like a straight line. Keep going. Micrometers. Now you're in a world where a speck of dust becomes a landscape. Fibers in fabric look like thick ropes. The surface of skin looks like ridges and valleys. But again, space still looks like a place where things sit with distances between them, with geometry that makes sense. Drop down to nanometers. Now you're at the scale of molecules. At this point, the idea of a solid surface begins to soften. Solids are not solid in the everyday sense. They are arrangements of atoms held in place by electromagnetic forces. The surface is a boundary where those forces change, not a perfectly sharp edge. Still, you can describe location. You can say an atom is here, another is there. You can measure average distances. The space between them exists and it can be discussed. Move down again. Picometers. This is around the scale of atoms themselves. Now you're in the strange territory where the old picture of tiny balls orbiting each other breaks down. Electrons are not little planets. They are described by wave-like probability distributions. Instead of saying, the electron is exactly here, quantum mechanics encourages you to say, the electron is likely to be found in this region if you measure it. This is the first place where shrinking begins to change not just what you see, but what you are allowed to claim. At atomic scales, the smoothness of space is not yet the main issue. The issue is that objects inside space behave differently. The The stage seems stable, but the actors don't stand still in the way everyday objects do. Still, we usually keep treating space as smooth because, for many purposes, it works. Quantum mechanics runs on equations that assume continuous space and time, even as it introduces uncertainty and probability for the things moving within that space. Now go smaller, down to the scale of nuclei femtometers. A femtometer is 1/quadrillionth of a meter. Protons and neutrons live here. Forces are intense. The strong nuclear force dominates. Yet we can still talk about distance and size in meaningful ways. Particles have interactions that depend on separation. Experiments can probe these scales. Space is still being treated as a continuous arena. Go smaller still. You enter the realm of particles that are not really particles in the classical sense, but excitations of fields, quarks and gluons. The language gets technical quickly here, but one point matters for our quiet shrinking exercise. At these scales, you can still do physics. You can still run experiments, predict outcomes, compare theory and measurement, and trust that smaller means something. Now keep shrinking and notice what changes. The smaller you try to go, the more energy you need to probe the region. This is not a detail, this is the hinge. To resolve small distances, you use high-energy particles. There's a simple relationship at play. Shorter wavelengths correspond to higher energies. If you want to see finer detail, you need a shorter wavelength probe. Light with long wavelengths like radio waves can't resolve tiny structures. Light with shorter wavelengths, like X-rays, can. If you want to probe even smaller than that, you go to even higher energies, and eventually you're using particle collisions. So each time you shrink your target, you turn up the energy of your probe. That energy doesn't just act like a flashlight. In relativity, energy and mass are intimately linked, and in gravity, mass and energy both curve space. At low energies, the curvature is negligible. At high energies, it becomes relevant. This is where the act of shrinking thought by thought begins to run into a deeper physical consequence. At some point, you cannot shrink your probe without turning it into a gravitational problem. Imagine trying to examine a tiny region so small that the energy required is concentrated into that region. If enough energy is packed into a sufficiently small volume, the region becomes dominated by gravity. In extreme cases, it can form a black hole. Not a huge black hole swallowing stars, but a tiny one defined by the same principle. The energy density becomes so high that spacetime curves in on itself, creating an event horizon. This is the universe's way of saying, your attempt to look closer has altered the thing you're looking at. Now our shrinking exercise becomes more than a mental game. It becomes a test of what physics allows. If you keep demanding smaller and smaller resolution, you keep raising the energy, and eventually you reach a point where the energy required to probe a region of size L would have a Schwarzschild radius comparable to L. That's a fancy way of saying the region would collapse into a black hole of roughly the same size as the region you're trying to resolve. When that happens, information can't escape in the usual way. The measurement becomes self-defeating. This is one reason the Planck scale emerges as a natural boundary. The Planck length is roughly the scale at which quantum mechanics and gravity become equally important. It's derived by combining fundamental constants: the speed of light, Planck's constant, and the gravitational constant. Those constants come from three different pillars of physics: relativity, quantum mechanics, and gravity. When you combine them, you get a length that isn't chosen by human convenience. It falls out of the structure of the theories themselves. When you take that Planck length and imagine a volume built from it, you get the Planck volume, a region so small that our current languages of physics are not designed to describe it cleanly. Now, while we're shrinking, it helps to pause and be careful with words. When people hear minimum volume, they sometimes imagine that space is made of tiny cubes, like a three-dimensional grid of pixels. That is one possible idea in some speculative theories, but it is not something we can say with certainty. The safer, more accurate statement is that below this scale, the concept of volume may stop working in the way we expect. It's a subtle difference, but an important one. If space is truly discrete, then there would be a smallest unit that cannot be subdivided, a literal minimum volume. If space is not discrete but still becomes fundamentally uncertain at small scales, then there may not be a smallest piece, but there would still be a smallest meaningful measurement. In that second case, the Planck volume is less like a brick and more like a limit on what can be resolved. Our shrinking thought experiment is really about that second idea, the smallest meaningful scale, the smallest region where the usual concept of geometry can still be applied without contradiction. So what happens when space stops being smooth and you continue shrinking anyway, mentally, not physically? What does your mind do with it? It starts to reach for analogies, because analogies are how we hold on to understanding when direct intuition fails. One helpful analogy, if used carefully, is to think about pictures on a screen. From far away, a screen looks like a continuous image. Colours blend smoothly, lines appear solid, but if you zoom in far enough, you see pixels. At that scale, asking for a line thinner than a pixel doesn't make sense in the same way. You can still approximate it, you can still represent it with patterns, but the idea of a thinner line has hit a structural limit. Now, do not take this too literally. Space is not a screen. It may not be arranged in pixels. But the analogy captures one important feeling. The idea that smoothness can be an emergent feature, something that appears when you're not too close. Another analogy is to think about a fluid. Water seems continuous. You can pour it, stir it, measure its volume, but if you zoom in far enough, water is molecules. The smoothness is an average over many particles. At a scale smaller than a molecule, water as water stops being defined. You're no longer describing a fluid, you're describing components. In the case of space, we don't know what the components are. That's the heart of the mystery, but the pattern may be similar. Smooth space may be what you get when you average over something deeper. Now, our shrinking exercise becomes a way of asking, what is the molecule of space, if such a thing exists? Different theories offer different candidates. Some suggest loops, networks, or discrete chunks. Some suggest that space arises from quantum entanglement patterns, where the relationships between quantum states produce the geometry we interpret as space. Some suggest that space is a kind of bookkeeping device, emerging from how information is structured. But before we reach for those ideas, it helps to sit with the direct implication of shrinking toward the Planck volume, the inability to define a sharp location. If you cannot measure below a certain scale, then the concept of exactly here becomes meaningless, not unknown, meaningless. This is a stronger claim. It says that the universe does not have a definite answer to the question in the way we want it to, because the framework that supports definite answers no longer applies. That's a difficult thought for the mind, because so much of our thinking relies on definite locations and definite boundaries. We are creatures who point, who label, who separate one thing from another. The idea that space might resist that separation at its deepest level feels like losing grip. But there is another way to frame it. It may not be a loss, it may be a clue about how reality is built. When you shrink down to scales where quantum fluctuations of geometry matter, the shape of space is no longer fixed. It's not just that you don't know the shape, it's that there isn't a single shape. There is a range of possibilities, and the universe's state involves a combination of them, a distribution rather than a single, crisp geometry. In everyday quantum mechanics, we accept that particles can be in superpositions of states. They can be in combinations of possibilities until measured. If space itself is subject to quantum rules, then geometry could also be in a superposition. Instead of the distance is exactly this, you might have the distance has a probability distribution. This is the point where shrinking becomes psychologically interesting. You're asking your mind to live without the comfort of definite distances, to imagine a region of space where even the question, how big is it, has a different kind of answer. And yet, there is something practical about this. It explains why our equations misbehave. When we treat space as smooth and continuous down to arbitrarily small scales, we get infinities in our calculations. Those infinities are not just mathematical annoyances. They suggest we are using the wrong description. If space is not smooth below a certain scale, then the infinities might disappear when we replace the smooth model with a better one. So in a quiet way, the Planck volume becomes a promise. It says, if you want to keep shrinking your understanding, you need new tools. Now let's continue the shrinking, but in a more structured way. Instead of zooming through units, imagine shrinking the entire observable universe. Not physically, just conceptually. Picture the universe as a sphere containing everything you can, in principle, observe. It is vast, and its size is measured in billions of light years. Now imagine compressing it in your mind, turning the universe into something smaller, like a giant balloon that you slowly deflate. As you do, galaxies move closer together. Distances shrink. Light would have less room to travel. If you kept compressing, the average density would rise. At some point, physics would start changing because the energy density would become high enough for new behaviors. Stars would not remain stable. Matter would not remain in ordinary forms. Eventually you approach conditions like the early universe, hot, dense, and governed by particle physics rather than chemistry. Keep compressing. You reach a point where the distinctions between particles blur. Energies become enormous. The known forces may unify. The universe becomes a place where the details of space-time geometry matter intensely. And then you hit the Planck regime, where our confidence drops sharply. This is not a failure of imagination. It is a boundary in our theories. At this scale, we cannot reliably say what the universe would look like, because look like assumes a background geometry that we can describe, but we can still make meaningful statements about what happens to our descriptions. When you shrink the universe toward the Planck volume, you're not just making distances smaller. You're changing the relationship between energy, gravity, and quantum uncertainty. Eventually, the gravitational field becomes so strong and so intertwined with quantum effects that you cannot separate space from what is happening in space. The stage and the actors become the same thing. This is why many physicists suspect that at the smaller scales, what we call space may be derived from something else, something more primitive. It could be a network of relationships. It could be an information structure. It could be a quantum state whose properties, when viewed at large scales, appear as geometry. That might sound abstract, but we can keep it grounded by returning to the basic idea. When you shrink toward the Planck volume, the familiar tools of measurement stop working. You can't send a probe without creating gravitational distortion. You can't define distances without invoking quantum uncertainty. You can't keep space smooth without running into contradictions. So the smooth space you live in is likely a large-scale approximation, one that emerges when the underlying fluctuations average out. In a sense, shrinking the universe thought by thought is like shrinking a story. At large scales, a story has a clear plot and a clear sequence. At smaller scales, you're looking at the words. Smaller still, the letters. Smaller still, the ink patterns. At some point, the story as a story disappears, not because it was never real, but because you are looking at a level where story is no longer the right description. Space might be like that. At human scales, it's a place. At cosmic scales, it's a geometry shaped by matter and energy. At the smallest scales, it may be something else entirely, something that only becomes space when you stop zooming. When people talk about measurement, it often sounds like something simple and mechanical. You point a device at something, read a number, and move on. In everyday life, measurement feels passive, almost invisible. A ruler doesn't change the length of a table. A clock doesn't disturb the flow of an afternoon. A scale doesn't care who steps on it. Measurement feels like observation without consequence. At the smallest scales of the universe, that quiet assumption falls apart. To understand why, it helps to slow down and rethink what measurement actually is. At its core, measurement is interaction. You never measure something by simply looking at it from afar in a neutral way. You always do something. You shine light. You send particles. You exchange energy. and whatever you are measuring responds to that interaction. At human scales, the response is negligible. The energy involved is tiny compared to the mass and structure of the object. The table doesn't notice the ruler. The clock doesn't care that you glanced at it. The universe, at these scales, is forgiving. But forgiveness runs out. As you shrink the scale of what you want to measure, the energy required to probe it increases. This is not a technological limitation. It's woven into the structure of physics. To resolve small distances, you need short wavelengths. Short wavelengths require high energies. There is no clever workaround that avoids this trade-off, so measurement becomes invasive. This is already familiar in quantum mechanics. When you measure the position of a particle precisely, you disturb its momentum. When you measure its momentum precisely, you lose information about its position. This isn't clumsiness, it's a rule. The uncertainty principle isn't about human error, it's about how nature behaves. At first, this uncertainty seems manageable. You accept that particles are fuzzy, that they don't sit at exact points the way marbles do. You learn to work with probabilities. Physics continues to function. But as the scale shrinks further, something new enters the picture. Gravity. Gravity is the weakest of the known fundamental forces, but it has a unique trait. It affects everything that has energy. And at very small scales, the energy you concentrate to perform a measurement becomes enormous relative to the size of the region you're probing. Imagine trying to pinpoint a location within an extremely tiny region of space. You send in a probe with a very short wavelength. That probe carries energy. That energy, confined to a small region, creates curvature in space-time. You're no longer measuring space as it was. You are reshaping it. At some point, the curvature becomes extreme. There is a threshold where the energy density required to measure a region is so high that the region collapses under its own gravity. Instead of revealing finer detail, your measurement creates a boundary beyond which information cannot escape. A horizon forms. The measurement ends not with clarity, but with concealment. This is the scale where measurement breaks down, not because we lack imagination or engineering skill, but because the act of measurement defeats its own purpose. This scale is intimately connected to the Planck length and Planck volume. It emerges when you combine three constants that normally live in separate corners of physics. The speed of light, which governs relativity, Planck's constant, which governs quantum mechanics, and the gravitational constant, which governs gravity. When you put them together, you get a length scale that is unimaginably small. More importantly, you get a signal. It tells you that below this scale, the usual separation between observer and observed no longer holds. At larger scales, you can pretend the measuring device is separate from what it measures. At the Planck scale, that separation dissolves. This is not because the universe becomes hostile to knowledge. It's because the structure of reality does not allow clean questions at that level. Asking for exact positions, exact distances, exact volumes becomes like asking for the exact colour of a shadow in complete darkness. The framework that supports the question is gone. One way to think about this is to consider how maps work. A map is a representation. It simplifies reality. You don't include every pebble or blade of grass. At some level of zoom, the map stops being useful. Not because the world stops existing, but because the representation no longer applies. Our physical theories are maps. General relativity is an extraordinarily accurate map of space-time at large scales and strong gravitational fields. Quantum mechanics is an extraordinarily accurate map of particles and fields at small scales and low gravitational influence. But when you try to use both maps at once, at the smallest possible scales, they overlap in a way that creates contradictions. General relativity assumes a smooth geometry. Quantum mechanics assumes fluctuations and uncertainty. When both are pushed to their extremes, the assumptions clash. The breakdown of a measurement is where this clash becomes unavoidable. Consider again the idea of probing smaller and smaller distances. Each time you shrink your target, you increase the energy of your probe. But energy doesn't just curve space, it also fluctuates quantum mechanically. At the smallest scales, the fluctuations in energy become large relative to the average energy itself, so now spacetime isn't just curved, it's fluctuating wildly. In this regime, the idea of a fixed background geometry disappears. There is no stable grid against which you can measure positions. The ruler itself is shaking, not metaphorically but physically. The distances between points fluctuate. The concept of between loses precision. This is why physicists say that below the Planck scale, spacetime may not be a smooth manifold at all. A manifold is a mathematical structure that allows you to define smooth coordinates and distances locally. It's the foundation of calculus and geometry. If spacetime ceases to be a manifold, then calculus stops working. Derivatives stop being meaningful. Continuous curves stop being well defined. That doesn't mean nothing exists there. It means the language of smooth geometry no longer applies. The breakdown of measurement is therefore also the breakdown of description. This is a difficult idea to accept, especially because science is often presented as a march toward ever finer detail. Better telescopes, better microscopes, higher resolution. But here, resolution hits a wall. Not a wall of ignorance, but a wall of meaning. It's tempting to imagine that future technology will simply push past this, that a more advanced civilization will build a better probe and measure smaller scales. But the Planck boundary is not a technological limit. It is a physical one, implied by the structure of the theories themselves. To get past it, you wouldn't just need better tools, you would need a different way of thinking about what measurement is. Some approaches to quantum gravity suggest that measurement at these scales must be relational. Instead of asking for absolute positions, you ask about relationships between entities. Instead of measuring space directly, you infer geometry from patterns of interaction. In these approaches, space is not something you measure. It is something that emerges from measurement-like processes at a deeper level. This idea can feel slippery, but it has a familiar echo. Consider how we infer the shape of a social network. You don't measure the network directly. You observe interactions, messages sent, connections formed, patterns emerge. The space of the network is not a physical thing, but it is real in a functional sense. Similarly, at the deepest scales, space may be inferred rather than observed. The breakdown of measurement also raises questions about objectivity. At large scales, different observers can agree on measurements once they account for relative motion. At the smallest scales, even that agreement may fail. Different ways of probing may not converge on the same answer, because there is no single underlying quantity to agree on. This doesn't mean physics becomes subjective, it means the structure of reality is more subtle than our usual categories. One important consequence of this is that the Planck volume may represent not a smallest chunk of space, but a smallest operationally definable region. It is the smallest region for which the concept of volume makes sense within our current framework. Below that, the word volume may not apply. This distinction matters. If there were a smallest chunk like a Lego brick of space, then space would be discrete in a simple way. You could count the bricks, but if there is only a smallest definable region, then space could be fundamentally relational or emergent, without discrete building blocks in the usual sense. Current physics does not settle this question. But the breakdown of measurement tells us where the question becomes unavoidable. Another way to appreciate this breakdown is to consider time. Measurement of space often relies on time. You send a signal and measure how long it takes to return. Distance is inferred from time and speed. But at very small scales, time itself becomes uncertain. Quantum mechanics allows for fluctuations in energy over short times. General relativity ties energy to the curvature of time as well as space. At the Planck scale, fluctuations in energy imply fluctuations in time itself. Clocks cannot tick reliably. The idea of a well-defined duration dissolves, so now both space and time are unstable. The coordinates you rely on to define events are no longer firm. This is why physicists often talk about space-time breaking down together. It's not that space alone becomes problematic, it's that the entire framework of measurement based on coordinates, distances, and durations loses coherence. Importantly, this breakdown does not happen abruptly. There is no sharp cliff where everything suddenly fails. Instead, there is a gradual erosion of reliability. As you approach the Planck scale, predictions become more sensitive to assumptions. Calculations produce divergences. Small changes in input lead to wildly different outputs. This sensitivity is a sign that you're using a theory outside its domain of validity. In everyday science, we're used to switching theories when conditions change. We don't use fluid dynamics to describe individual molecules. We don't use classical mechanics to describe electrons. We accept that different scales require different descriptions. The Planck scale suggests that we need another switch. But until that new framework is complete, the breakdown of measurements serves as a guidepost. It tells us where our current theories stop being trustworthy. It tells us where space stops being something we can probe without fundamentally altering it. There is something quietly humbling about this. It reminds us that the universe is not obligated to reveal itself at every scale in the same way. It has layers of description, each with its own domain of usefulness. At the scale where measurement breaks down, we are not peering into nothingness. We are standing at the edge of a map, aware that the territory continues, but knowing that the symbols we've been using are no longer adequate. This awareness doesn't end the journey, it redirects it. If measurement cannot reach smaller scales directly, then understanding must come indirectly, through consistency, through unification, through theoretical structures that reduce to known physics at larger scales while remaining well-behaved at smaller ones. That is why the Planck scale is not just a curiosity, it is a constraint. Any successful theory of fundamental reality must respect it. It must explain why measurement fails there and what replaces it. As we continue, this idea will keep resurfacing. The breakdown of measurement is not an isolated problem. It connects to the nature of space, the behavior of time, the role of gravity, and the question of whether the universe has a minimum volume at all. Those connections unfold naturally once we sit with the idea that shrinking the universe eventually forces us to confront not smaller things, but different rules. And those rules, whatever they are quietly waiting beyond the scale where measurement itself can no longer guide us directly. When the phrase Planck volume comes up, it has a way of sounding more concrete than it really is. The word volume suggests something you could point to, a tiny box, a microscopic container of space sitting somewhere deep beneath atoms and particles. It invites the mind to imagine a smallest cube, neatly defined, waiting at the bottom of reality like the final tile in a mosaic. That picture is understandable, is also misleading. To really understand what the Planck volume is, and just as importantly what it is not, we need to take a careful step back and examine where it comes from, what role it plays in physics, and why it shows up so reliably whenever we push our theories to their limits. The Planck volume is derived, not discovered. No one has observed it directly. No experiment has isolated it. Instead, it emerges when physicists combine a small set of fundamental constants that describe how the universe behaves at its deepest known levels. Those constants come from very different corners of physics. One governs the structure of space and time at high speeds, another governs the behavior of matter and energy at very small scales, another governs gravity, the slow but universal influence that shapes the cosmos. When you combine them in the only way that produces a quantity with the dimensions of length, you get the Planck length. When you take that length and imagine a region defined by it in 3 dimensions, you get the Planck volume. This process alone already tells you something important. The Planck volume is not introduced because someone measured a smallest region of space. It appears because the mathematics of our best theories start pointing to a scale where their assumptions collide. It is a boundary marker, not a building block. The Planck length is unimaginably small, far beyond anything we can currently probe. To put it into perspective without relying on poetic exaggeration, it is many orders of magnitude smaller than the size of a proton. If a proton were expanded to the size of the observable universe, the Planck length would still be smaller than a grain of sand in that expanded universe. These comparisons are clumsy, but they give a sense of just how far removed this scale is from direct experience. The Planck volume, being the cube of that length, is even more extreme. But again, size alone is not the main point. The significance of the Planck volume lies in what happens to our descriptions of space when we approach it. One of the most common misunderstandings is the idea that the Planck volume is the smallest possible chunk of space, like an indivisible atom of geometry. While some speculative theories do explore that possibility, it is not something established by physics as it currently stands. There is no experimental evidence that space is literally made of Planck-sized cubes packed together. Instead, the safer and more accurate way to think about the Planck volume is as the smallest region of space for which our existing concepts of geometry, distance and volume can be applied without contradiction. Below this scale, the words still exist, but their meaning becomes unreliable. To see why this distinction matters, consider how we usually talk about limits in science. Sometimes a limit reflects a physical boundary. You cannot compress ordinary matter beyond a certain point without changing its state. You cannot exceed the speed of a light with objects that have mass. These are physical limits in the sense that nature enforces them directly. Other limits are conceptual. Temperature, for example, is not defined for a single molecule. That does not mean the molecule does not exist. It means the concept of temperature does not apply at that scale. Temperature emerges when you consider many particles together. The Planck volume is closer to this second kind of limit. It may be that space continues to exist below the Planck scale in some form, but not in a way that can be meaningfully described as volume in the geometric sense we are used to. The Planck volume marks the scale at which geometry itself may stop being fundamental. This idea is reinforced by how the Planck scale appears in calculations. When physicists attempt to compute physical quantities such as energy densities or interaction strengths at extremely small distances, the equations often produce infinities. These infinities are not just mathematical curiosities. They signal that the theory is being applied outside its domain of validity. If space were truly smooth and continuous all the way down, these infinities would suggest catastrophic behavior at small scales. But the fact that the same scale keeps appearing as a cutoff suggests something else. It suggests that smoothness is an approximation that fails beyond a certain point. The Planck volume, then, acts like a warning sign embedded in the equations. It tells us where the map stops being trustworthy. Another common misconception is that the Planck volume is something that exists independently, waiting quietly beneath everything else. In reality, its meaning depends entirely on the framework used to define it. It arises from combining constants that already encode assumptions about space, time, and measurement. This is subtle but important. The Planck length depends on the speed of the light, which assumes a relativistic structure of space-time. It depends on Planck's constant, which assumes quantum uncertainty. It depends on the gravitational constant, which assumes a geometric theory of gravity. If any of these assumptions change, the Planck scale changes with them. This means the Planck volume is not a universal brick in the way an electron or a quark is. It is a scale defined within a particular theoretical context. That context happens to be extraordinarily successful, which is why the Planck scale is taken seriously. But it is still a context, not a direct observation. So what does the Planck volume actually represent? At its core, it represents the smallest region of space for which it makes sense to talk about volume without needing a theory of quantum gravity. It is the scale at which quantum effects of gravity can no longer be ignored. Above it, gravity can often be treated classically, and quantum mechanics can be applied on a fixed background. Below it, that separation breaks down. In other words, the Planck volume is the scale where the stage and the actors become inseparable. This has practical consequences. At larger scales, You can treat space as something that exists independently of what happens within it. You can calculate particle interactions against a fixed geometry. You can treat gravity as a smooth curvature that responds to averaged energy distributions. At the Planck scale, none of that works. Energy fluctuations are so large that they distort geometry significantly. Geometry fluctuates in response. There is no fixed background on which events unfold. Space itself becomes part of the quantum system. In this regime, asking how big is this region is like asking where exactly is this wave, without specifying how you intend to measure it. The answer depends on the measurement, and the measurement changes the system. This is why many physicists say that the Planck volume is not something you can occupy. You cannot put an object inside it. You cannot imagine shrinking yourself down and standing within a Planck-sized box. That image assumes a stable background that no longer exists at that scale. The Planck volume is not a place. It is a condition. Another important clarification is that the Planck volume is not necessarily the smallest possible volume, only the smallest meaningful one given our current understanding. This leaves open several possibilities. One possibility is that space really is discrete, with a smallest indivisible unit, and that the Planck volume corresponds roughly to that unit. In this case, space would be fundamentally granular, even if that granularity is invisible at larger scales. Another possibility is that space is continuous, but quantum fluctuations make it impossible to define volumes smaller than a certain scale with any consistency. In this case, there is no smallest unit, only a smallest resolution. A third possibility is that space itself is emergent, arising from more fundamental entities that are not spatial in nature. In this scenario, the Planck volume marks the scale at which the emergent description fails, not because space breaks into pieces, but because space was never fundamental to begin with. Current physics does not choose between these possibilities. Different approaches to quantum gravity favour different answers. What they share is the recognition that the Planck scale is where something profound changes. It is also worth noting what the Planck volume is not responsible for. It does not by itself explain why space has 3 dimensions. It does not explain why the universe has the size it does. It does not act as a container for energy or matter. It does not behave like a particle. It is tempting to load it with significance because of how exotic it sounds. But the Planck volume is modest in its role. It sets a scale. It tells us where certain approximations stop working. It does not dictate the detailed structure of reality beyond that. One helpful way to keep expectations grounded is to compare the Planck volume to the concept of absolute zero temperature. Absolute zero is a limit defined by thermodynamics. You cannot reach it, but you can approach it. It marks the point where classical ideas of heat motion cease to apply cleanly. Similarly, the Planck volume marks a limit where classical ideas of space cease to apply cleanly. You can approach it in theory, but once you are there, the language of geometry needs to be replaced or extended. There is also an important psychological aspect to all of this. Humans like smallest things. We like final answers. We like the idea that if we just keep looking closer, we will eventually reach the bottom layer and say, this is it. The Planck volume resists that desire. It suggests that the universe may not have a simple bottom layer in spatial terms. Instead, it may have a bottom layer in descriptive terms, a point beyond which the concept of space itself is no longer the right tool. This can feel unsatisfying at first. It feels like the universe is withholding something. But another way to see it is that the universe is inviting a different kind of understanding, one that does not rely on carving reality into ever smaller boxes. The fact that the Planck volume emerges from the interplay of constants also hints at something deeper. It suggests that space, time, energy, and gravity are not independent ingredients, but aspects of a single structure. The Planck scale is where those aspects become inseparable. At everyday scales, we can afford to treat them separately. We can talk about space without worrying about time dilation. We can talk about particles without worrying about gravitational collapse. The universe allows these simplifications because the effects are small. At the Planck scale, the simplifications are no longer allowed. This is why the Planck volume appears in discussions of black holes, the early universe, and the unification of forces. In all of these cases, energy densities become extreme and the usual separations fail. It is also why the Planck volume plays a role in debates about whether the universe has a minimum volume at all. If space cannot be meaningfully defined below this scale, then in an operational sense there is a minimum volume, not because nothing exists below it, but because no experiment can distinguish one configuration from another at that scale. That distinction matters deeply for how we think about reality. A minimum meaningful volume is not the same as a minimum existent volume. It is a statement about knowledge, not necessarily about being. It says something about what the universe allows to be defined, not about what it allows to exist. As we move forward, this idea will keep resurfacing. The Planck volume will show up again when we talk about whether space might be quantized, how gravity behaves at small scales, and what the early universe may have been like when everything was compressed to extreme densities. For now, it is enough to hold on to a careful understanding. The Planck volume is not a tiny box. It is not a building block. It is not a place you can imagine standing inside. It is a scale where our familiar ideas of measurement, geometry, and volume lose their independence and must be replaced by something deeper. And once that is clear, it becomes easier to ask the next question. If the Planck volume is not a smallest brick of space, then why do so many theories still hint that space might come in pieces at all? What motivates the idea that space could be discrete, and what does that actually mean when examined closely? The idea that space might come in tiny pieces can sound strange at first, almost like borrowing language from digital screens or building blocks and trying to apply it to the universe itself. We are used to thinking of space as something continuous, something that stretches smoothly in every direction without interruption. That intuition is deeply rooted in daily experience. You can walk across a room without jumping over gaps. You can draw a line on paper and make it as smooth as your hand allows. Nothing in ordinary life suggests that space itself might be made of discrete units. And yet, physics has learned to be cautious about trusting everyday intuition too far. The suggestion that space might not be infinitely divisible does not come from a desire to make reality more exotic. It comes from repeated encounters with limits, inconsistencies, and unanswered questions that arise when we insist on treating space as perfectly smooth at all scales. Over time, different lines of reasoning developed independently have begun pointing in a similar direction. They don't prove that space is discrete, but they make the idea difficult to ignore. To understand why this idea keeps resurfacing, it helps to start with something familiar: matter. For most of human history, matter was thought to be continuous. A piece of wood could be divided into smaller pieces, and those into smaller ones, seemingly without end. The idea that matter might be made of indivisible units was debated for centuries, often more as philosophy than science. When atoms were finally established as real, it wasn't because people wanted discreteness. It was because continuous models failed to explain observations. The discreteness of matter solved problems. Energy faced a similar transition. At the end of the 19th century, physicists expected energy to vary smoothly. But experiments involving heat radiation and light emission refused to cooperate. The solution was quantization. Energy, in certain contexts, comes in discrete packets. This wasn't a stylistic choice. It was forced by evidence. Space has not yet gone the same experimental reckoning, but the pattern is suggestive. Whenever physics has tried to push a continuous description beyond its natural range, discreteness has appeared, not as an assumption, but as a remedy. One of the earliest reasons physicists began to consider discrete space came from attempts to unify quantum mechanics and gravity. These two frameworks are remarkably successful in their own domains, but they are structurally incompatible in important ways. Quantum mechanics relies on probabilities, uncertainty and fluctuations. General relativity relies on smooth geometry and continuous curvature. When you try to apply quantum principles to gravity directly, treating the gravitational field as something that fluctuates quantum mechanically, the mathematics quickly becomes unstable. Calculations produce infinities that cannot be removed by the usual techniques. These infinities are not minor technical issues. They indicate that the theory is being applied in a regime where its assumptions are no longer valid. One way to tame infinities in physics is to introduce a smallest scale. If space cannot be divided indefinitely, then certain pathological behaviours disappear. Integrals that would otherwise blow up are naturally cut off. Fluctuations are limited. Quantities remain finite. This does not prove that space is discrete, but it makes discreteness an attractive possibility. Another motivation comes from information theory. In modern physics, information is not just an abstract concept, it is tied to physical systems. Storing information requires energy. Transmitting information takes time. There are limits to how much information can be packed into a given region of space. One of the most striking results in this area comes from the study of black holes. Black holes are not just gravitational traps, they have thermodynamic properties. They have entropy. That entropy turns out to be proportional not to the volume of the black hole, but to the area of its boundary. This result is deeply counterintuitive. In most systems, entropy scales with volume. More space means more ways to arrange things, but black holes seem to encode information on surfaces. This observation has led to the idea that the fundamental degrees of freedom of space might also scale with area rather than volume. If the amount of information that can be stored in a region of space is finite, then that region cannot support infinitely many independent degrees of freedom. That, in turn, suggests that space itself may have a finite number of fundamental elements within any given volume. In other words, infinite smoothness may be incompatible with finite information capacity. This idea is sometimes expressed through the holographic principle, which proposes that the information content of a volume of space can be described by data on its boundary. While this principle does not require space to be discrete in a simple grid-like way, it does imply that space is not infinitely rich at arbitrarily small scales. There is also a more operational argument for discreteness that comes from thinking about measurement again, but from a slightly different angle. Imagine trying to define a coordinate system with infinite precision. To do so, you would need markers, clocks, and rulers that are arbitrarily small and arbitrarily precise. But as we have seen, creating such devices requires energy, and energy affects space-time. At some point, the attempt to refine your coordinate system destroys its own reference frame. If no operational procedure can distinguish between two locations separated by less than a certain distance, then those locations are physically indistinguishable. From the point of view of physics, indistinguishable states are often treated as identical. This is not philosophical hair-splitting. It is a practical rule used throughout quantum mechanics. If two states cannot be distinguished by any measurement, they are represented by the same state in the theory. Applying this reasoning to space suggests that distances below a certain scale may not correspond to distinct physical situations. That does not necessarily mean space is made of blocks, but it does mean that space does not support infinite resolution. Another place where the idea of discrete space appears is in attempts to formulate gravity using quantum principles directly. Some approaches start by abandoning the idea of smooth geometry altogether. Instead of assuming space exists first and then placing fields on top of it, they build space from more primitive elements. In these frameworks, space is not fundamental. It emerges from networks, graphs, or relationships. Nodes are connected by links. Geometry arises from patterns of connection rather than from pre-existing coordinates. In such pictures, discreteness is not imposed. It is built in from the start. The motivation here is not aesthetic, it is practical. If you want a theory that does not rely on smooth spacetime, you must replace it with something else. Discrete structures are mathematically well defined. They avoid infinities naturally. They allow for well-behaved quantum descriptions. Still, it is important to be precise about what discrete means in this context. It does not necessarily mean that space is arranged like a lattice you could draw on graph paper. Many discrete structures do not resemble grids at all. They can be irregular, relational, and dynamic. Discreteness, in this sense, means that there is a finite amount of structure per unit of scale. It means that you cannot subdivide indefinitely without running out of distinguishable features. This brings us back to the Planck volume. If the Planck volume represents the smallest region that can be meaningfully discussed using geometric language, then it naturally invites the idea that space might come in units of roughly that scale. Not because nature prefers cubes of that size, but because any attempt to describe smaller subdivisions loses physical meaning. This is similar to how sound waves behave. At large scales, you can describe sound as a continuous wave travelling through air. At smaller scales, you must acknowledge that sound is made of individual molecular collisions. Below that, sound as a concept ceases to apply. Space might behave the same way. Smooth geometry might be a large-scale description of something that, at smaller scales, is structured differently. Another reason discreteness is appealing comes from the desire for consistency across physics. Quantum mechanics treats many quantities as quantized. Fields are made of quanta. Energy levels are discrete in bound systems. If gravity and spacetime are to be quantized as well, it would be surprising if space alone remained infinitely divisible, while everything else became granular. This is not a proof, but it is a pattern. Patterns matter in physics because they often hint at deeper unity. However, there are also strong reasons to be cautious. Discrete space introduces its own challenges. It can break symmetries that are well supported by experiment, such as rotational invariance or Lorentz invariance, if not handled carefully. A simple grid of space would privilege certain directions which we do not observe. Any viable theory of discrete space must recover the appearance of smoothness and symmetry at large scales. This is a non-trivial requirement. It means that discreteness, if it exists, must be subtle. This is why many physicists prefer to say that space might be effectively discrete, rather than literally composed of chunks. The distinction matters. Effective discreteness means that below a certain scale, distinctions blur, measurements saturate, and new descriptions take over, even if there is no literal tiling of space. In this view, asking whether space is discrete or continuous may be the wrong question. The more relevant question may be whether space is fundamental or emergent. If space is emergent, then its small-scale structure does not have to resemble space at all. The pieces would not be spatial pieces. They would be elements of whatever deeper theory gives rise to spatial relationships at larger scales. This reframing helps resolve some of the tension. Space might not come in tiny pieces the way matter does. Instead, space might arise from tiny pieces of something else. That something else could be quantum states. It could be informational relationships. It could be algebraic structures that only resemble geometry, when many of them are considered together. What ties all of these ideas together is the repeated appearance of limits. Limits on measurement, limits on information, limits on resolution, limits on how much structure can exist in a given region without contradiction. These limits are not arbitrary, they cluster around the same scale. That clustering is the reason physicists keep returning to the idea of tiny pieces, not because the idea is comforting or intuitive, but because it keeps offering a way out of deep theoretical trouble. There is also a quiet philosophical shift hiding in this discussion. For a long time, physics assumed that space and time were the stage on which everything else happened. Matter and energy were the actors. Discreteness, when it appeared, applied to the actors. Now the stage itself is being questioned. If space comes in pieces, or emerges from something discrete, then the distinction between stage and actor dissolves. Geometry becomes dynamic. Structure becomes relational. the universe becomes less like a theatre and more like a process. This is a challenging idea, but it has a certain coherence. It aligns with the breakdown of measurement. It aligns with the Planck scale. It aligns with the strange behaviour of black holes and the early universe. It also aligns with a broader lesson physics has learned repeatedly. When we push a concept beyond where it works, the universe does not politely extend it. It forces us to replace it. Whether space truly comes in tiny pieces remains an open question, but the reasons for considering it are not speculative in the casual sense. They arise from concrete problems that refuse to go away. Gravity is often introduced as the calmest of the fundamental forces. It acts quietly, steadily, almost politely. It keeps planets in their paths, holds atmospheres close to worlds, and shapes galaxies over billions of years without drawing much attention to itself. Compared to the violent flashes of electromagnetism or the intensity of nuclear forces, gravity seems almost gentle. That gentleness is deceptive. At ordinary scales, gravity is weak. You need an entire planet to notice it properly. But gravity has a trait that becomes overwhelming when conditions are right. It does not switch off. It responds to all forms of energy without exception, and it reshapes the very stage on which everything else happens. When we begin to talk about the smallest possible volumes of space, gravity refuses to stay in the background. To understand why, it helps to recall what gravity actually is according to our best description. In general relativity, gravity is not a force pulling objects together across space. It is the curvature of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. This relationship works beautifully at large scales. It predicts the bending of light around stars, the slowing of time near massive objects, and the expansion of the universe itself. Crucially, general relativity assumes that space-time is smooth. It can be curved, stretched, and warped, but it is still treated as a continuous geometric structure. You can zoom in on a small region and approximate it as flat. You can define distances, angles, and volumes locally. Quantum mechanics, on the other hand, is built on a very different foundation. It describes a world where fluctuations are unavoidable. Energy cannot be perfectly still. Fields do not sit quietly at zero. Even in the lowest possible energy state, there are fluctuations. This is known as zero-point energy, and it is not optional. It is a consequence of the uncertainty principle. When quantum mechanics is applied to particles moving through space, this restlessness is manageable. The particles fluctuate, the fields fluctuate, but space itself is treated as a fixed background. The stage may be curved by gravity, but it does not fluctuate quantum mechanically in standard quantum field theory. That separation is where the trouble begins. When you attempt to apply quantum principles to gravity itself, you're no longer dealing with particles fluctuating within space. You're dealing with space fluctuating. This is where the idea of quantum foam enters the picture. The term quantum foam was introduced as a way to describe what space-time might be like at extremely small scales, near the Planck length. The word foam suggests something bubbling, irregular, constantly changing. While the image is imperfect, it captures a key idea. At very small scales, space-time may not be smooth and serene, it may be restless. To see why this is expected, consider what quantum mechanics demands. If gravity is associated with energy, and energy fluctuates, then gravity must fluctuate as well. And since gravity is geometry, geometry must fluctuate. These fluctuations are not gentle ripples. At the Planck scale, they are expected to be violent relative to the size of the region involved. Distances would not be sharply defined. Volumes would not remain constant. The very notion of a fixed metric, a stable way to measure geometry, would fail. This is a radical departure from how we normally think about space. In everyday experience, space is passive. It does not jitter. It does not change its shape from moment to moment. Even in strong gravitational fields, changes are smooth and predictable. But quantum mechanics does not allow for perfect stillness. It demands activity, even in the absence of matter. So when gravity and quantum mechanics meet at the smallest scales, the result is a geometry that cannot sit still. Imagine trying to define the distance between 2 points in such a regime. At one moment, the distance might be slightly larger, at another moment, slightly smaller. Not because the points moved, but because the geometry connecting them fluctuated. There is no single answer. There is a distribution of possibilities. This is what is meant by restless geometry. It is important to emphasize that this restlessness is not something that happens over time in the usual sense. Time itself is part of the fluctuating structure. These are not changes happening within a stable timeline. They are features of the underlying quantum state of spacetime. This makes the situation difficult to visualize, but we can still reason about its consequences. One immediate consequence is that the concept of a smooth manifold breaks down. A manifold is a mathematical object that allows you to define coordinates locally and perform calculus. It assumes that at sufficiently small scales, space looks flat. Quantum foam challenges that assumption. There may be no scale at which geometry becomes simple and smooth. Instead of a calm surface that can be approximated as flat when you zoom in, you may have a constantly fluctuating structure, where zooming in reveals more complexity, not less. This is where gravity changes character. At large scales, gravity is deterministic. Given enough information, you can predict how objects will move. At the Planck scale, gravity becomes probabilistic. It is no longer a smooth curvature, but a quantum field with uncertainty. This does not mean gravity becomes random in a chaotic sense. It means that it must be described statistically, like other quantum phenomena. Geometry itself becomes a quantum object. This has profound implications for the idea of a minimum volume. If geometry fluctuates wildly at small scales, then the idea of a fixed, well-defined volume becomes suspect. A region of space cannot be assigned a single volume if the geometry itself is uncertain. Instead, volume becomes an operator, something with a range of possible values. In some theoretical frameworks, the volume of a region is quantized. It can take on discrete values, much like energy levels in an atom. In others, volume is continuous, but subject to large fluctuations that make precise values meaningless below a certain scale. Either way, the calm picture of space as a stable container fails. Quantum foam also challenges the idea of locality. Locality is the principle that interactions happen at specific points in space and time, and that influences propagate through space at finite speeds. This principle underlies much of physics and aligns well with everyday intuition. At the smaller scales, locality may blur. If geometry fluctuates, then the notion of near and far becomes fuzzy. 2 points that appear close in one geometric configuration might be farther apart in another. Connections between regions may be transient. The network of relationships that define space may reconfigure constantly. This does not mean that causality is violated in the usual sense. It means that the background structure that supports local interactions is itself dynamic. This is why some physicists prefer to think in terms of networks rather than continuous space. In these views, space is a pattern of connections that can rearrange. Distance is not fundamental. It emerges from how strongly or weakly different elements are connected. In such a picture, gravity is not something added on top of space. It is a manifestation of how those connections change. The foam-like behavior is not something we would ever experience directly. At human scales, the fluctuations average out. Just as the surface of a liquid looks smooth from afar despite being made of constantly moving molecules, space looks smooth because we are so far above the scale where its restlessness matters. This averaging is why general relativity works so well. General relativity is not wrong. It is incomplete. It is a large-scale approximation of a deeper, more restless structure. At scales where quantum fluctuations of geometry are negligible, the smooth description is accurate. The trouble comes when we try to extend that description too far. One of the reasons black holes play such a central role in these discussions is that they force geometry into extreme conditions. Near a black hole's core, curvature becomes enormous. Energy densities skyrocket. Classical descriptions predict singularities, points where curvature becomes infinite. Most physicists believe these infinities are not real. They are signs that the smooth geometric description has failed. At those scales, quantum foam-like behavior should dominate, preventing the formation of true singularities. In this sense, quantum foam may act as a kind of regulator. It prevents geometry from collapsing into mathematical absurdities. It replaces singular points with highly fluctuating but finite structures. The early universe presents a similar challenge. When the universe was extremely young and dense, energy densities were enormous. Classical cosmology predicts a singular beginning. Quantum gravity suggests that this beginning may not be a singular point, but a regime of intense geometric fluctuation. In both cases, gravity is not calm. It is active, restless, inseparable from quantum uncertainty. Another subtle implication of restless geometry is that the distinction between space and matter becomes blurred. If geometry fluctuates quantum mechanically, then the difference between empty space and something happening becomes less clear. Fluctuations of geometry carry energy. Energy curves geometry. The loop feeds back on itself. This self-referential nature makes quantum gravity notoriously difficult to formulate. You cannot place quantum fields on a fixed background if the background itself is a quantum field. This is why so many attempts at quantum gravity involve radical rethinking. Some approaches quantize geometry directly. Others avoid geometry altogether at the fundamental level and recover it later. Others reframe gravity as an emergent phenomenon arising from more basic quantum principles. What they share is the recognition that gravity at the smallest scales is not gentle. It is not something you can ignore. It is the driver of geometric instability. The phrase quantum foam can make this sound chaotic, but it is worth resisting that impression. Chaos implies unpredictability in the classical sense. Quantum foam implies uncertainty governed by well-defined rules. The fluctuations are not arbitrary. They are constrained by quantum principles. The challenge is that we do not yet know those rules in their final form. What we do know is that restless geometry changes how we should think about the Planck volume. It is not a static cell of space. It is not a tiny room where physics continues as usual at smaller scales. It is a regime where geometry itself is dynamic and uncertain. In that regime, space is not something you inhabit. It is something that happens. This reframing helps make sense of why the Planck volume appears as a boundary. Below this scale, the idea of a fixed volume ceases to apply because volume itself fluctuates. It also explains why so many descriptions use probabilistic language. You do not ask, what is the volume? You ask, what is the distribution of possible volumes? You do not ask, what is the distance? You ask, what range of distances is consistent with the quantum state? This is a profound shift in perspective. At large scales, geometry feels solid. At small scales, it feels negotiable. The universe does not become meaningless at small scales. It becomes more subtle. And in that subtlety, the idea of a minimum volume is no longer about smallest pieces, but about the limits of calm geometry. It is about the point where space stops being a quiet backdrop and becomes an active participant in the quantum story. That active participation sets the stage for the next question. If geometry itself is restless, then how do we even talk about distance in such a regime? What does it mean for 2 points to be separated when the space between them refuses to stay still? Distance feels like one of the most basic ideas we have. Two things are either close together or far apart. You can reach something or you can't. You can measure how long it takes to walk somewhere, how much space fits between two objects, how far a sound travels before it fades. Distance feels immediate, intuitive, almost physical in the most straightforward sense. and because it feels so fundamental, it's easy to assume that distance must remain meaningful, no matter how deeply we probe the universe. Even if particles behave strangely, even if energy fluctuates, surely space itself must still provide a reliable notion of separation. That assumption turns out to be fragile. To see why, it helps to examine what distance really is, stripped of habit and convenience. Distance is not something you observe directly. You never experience distance by itself. You infer it from processes. Light travels from one place to another. A signal is sent and received. An object moves and takes time to get somewhere. Distance is always tied to something happening. In classical physics, this relationship is stable. Space provides a fixed background. Time flows uniformly, and signals propagate predictably. You measure distance by timing how long light takes to travel, or by laying down a ruler, or by counting steps. All of these methods rely on the assumption that space is calm and geometry is stable. As we move toward the smallest scales, that assumption begins to erode. Earlier, we explored the idea that geometry itself becomes restless due to quantum effects. When geometry fluctuates, distance cannot remain a fixed quantity. If the structure of space changes from moment to moment, then the separation between 2 points is no longer a single number. It becomes a range of possibilities. This is not merely a matter of uncertainty in measurement. It is uncertainty in the thing being measured. Imagine trying to measure the distance between 2 markers placed on a surface that is constantly rippling. You might get one value at one instant and another value an instant later, even if neither marker has moved. The distance changes because the surface changes. At everyday scales, space does not ripple in this way. But near the Planck scale, fluctuations in geometry are expected to be large, relative to the distances involved. There is no longer a stable metric, no fixed ruler built into reality. This is the first way distance begins to lose meaning. But the story goes deeper. Distance is usually defined in terms of coordinates. You assign numbers to locations and compute separations between them. Coordinates, however, are a mathematical convenience. They are not physical objects. They only work because the underlying geometry supports them. In general relativity, coordinates are already treated with suspicion. Different coordinate systems can describe the same physical situation. There is no preferred grid imposed by the universe. Geometry is relational rather than absolute. At small scales, this flexibility becomes a problem rather than a feature. If geometry fluctuates quantum mechanically, then no coordinate system remains stable long enough to define precise separations. Coordinates become fuzzy. Transformations between coordinate systems are no longer smooth. The mathematical machinery that supports distance calculations breaks down. This is why many approaches to quantum gravity abandon coordinates altogether at the fundamental level. They replace them with relationships. In these approaches, distance is not something that exists first and then connects objects. It is something that emerges from how objects interact. 2 entities are close if they interact strongly, and far if they interact weakly. Geometry arises from the pattern of interactions, not the other way around. This is a radical shift, but it mirrors a pattern we have seen before. Consider how we think about social distance. 2 people might live in different cities, but interact constantly. Others might live next door and never speak. Physical distance is not the best measure of connection. Social distance is defined by interaction, not by meters. At the smallest scales of physics, spatial distance may behave more like social distance than physical distance. What matters is not where something is in an abstract geometric sense, but how it relates to other things. This perspective helps explain why distance loses its absolute meaning near the Planck scale. If geometry is emergent, then distance is not fundamental. It is a derived quantity that only makes sense when the underlying structure supports stable relationships. Another way distance loses meaning is through the role of energy. As we've seen, measuring small distances requires high energies. High energies distort geometry through gravity. This creates a feedback loop. To measure distance, you inject energy. The energy changes the distance you're trying to measure. At some point, this loop becomes uncontrollable. If you try to define a distance smaller than the Planck length, the energy required creates a gravitational disturbance comparable to that distance. The notion of a smaller separation collapses. You cannot operationally distinguish between 2 points separated by less than that scale. From the point of view of physics, indistinguishable situations are treated as equivalent. If no experiment can tell the difference between two separations, then the theory does not assign them different values. Distance, at that scale, is not just unknown, it is undefined. This distinction is subtle, but crucial. Unknown means there is a value we do not know. Undefined means there is no value to know. Distance losing meaning does not mean that the universe becomes vague or arbitrary. It means that the universe does not answer certain questions in the way we expect, because those questions assume a structure that no longer applies. This can feel unsettling because distance is so deeply woven into how we think. We imagine points, lines, separations, boundaries. We picture the universe as a vast container filled with objects at various locations. But that picture may be an approximation that works only above a certain scale. At the smallest scales, the universe may not be organized around location at all. Another reason distance becomes problematic is the role of quantum superposition. In quantum mechanics, particles can exist in superpositions of states. They do not have definite properties until measured in a particular way. If geometry itself is subject to quantum rules, then spatial relationships can also exist in superpositions. This means that two regions of space might be neither definitively near nor definitively far. They might be in a superposition of separations. Only when a particular interaction occurs does a specific distance become relevant. This is difficult to imagine because our minds are trained to think in terms of fixed layouts. But the mathematics of quantum theory does not forbid it. In fact, it naturally allows it. If distance can be in superposition, then the idea of a single, well-defined spatial arrangement dissolves at the smallest scales. Space becomes a collection of possibilities rather than a fixed stage. Another way to approach this is through the idea of minimal length. Many approaches to quantum gravity suggest that there is a minimum measurable length. This does not necessarily mean that space is discrete. It means that any attempt to probe shorter distances yields the same result. The resolution saturates. Think of a camera that has reached its maximum resolution. No matter how much you zoom in digitally, you do not reveal new detail, you just magnify pixels. The image does not become sharper. At the Planck scale, distance behaves like that. You can try to zoom in conceptually, but the universe does not reveal finer structure. The distinction between a little closer and a little farther stops making sense. This saturation of resolution is another way distance loses meaning. Distance also relies on time. Many distance measurements are based on timing signals. If time itself becomes uncertain at small scales, then distance measurements become doubly problematic. Quantum fluctuations in energy imply fluctuations in time. General relativity ties time to geometry. If time does not flow smoothly, then distances inferred from time delays become unreliable. At the Planck scale, the idea of a smooth timeline breaks down alongside the idea of smooth space. Without stable time, distance has no foundation. This is why physicists often speak of space-time rather than space alone. Distance and duration are two sides of the same coin. When one loses meaning, the other follows. Another consequence of distance losing meaning is the breakdown of locality. Locality is the principle that interactions occur at specific locations and propagate through space. It underlies causality as we normally understand it. Causes precede effects, and influences travel through space at finite speeds. If distance becomes fuzzy, then the idea of strictly local interactions becomes less clear. Interactions may not be confined to sharply defined points. Instead, they may involve regions with uncertain boundaries. This does not imply that causality disappears, it implies that causality may be encoded in a different way, not tied to precise spatial separations. Some theoretical frameworks suggest that causality might be more fundamental than space. Instead of space determining which events can influence each other, causal relationships might give rise to the appearance of space. In such views, distance is a summary of causal structure, not a primitive concept. This inversion of perspective helps explain why distance might not survive as a fundamental notion at the smallest scales. At large scales, causality and geometry align neatly. Signals travel through space and distance matters. At small scales, causality might persist even as geometry fluctuates wildly. Distance becomes an emergent bookkeeping tool rather than a foundational ingredient. Another subtle point is that distance assumes separability. To talk about distance between two things, you must be able to identify them as distinct. At the smallest scales, separability itself becomes questionable. Quantum entanglement links systems in ways that defy classical separation. Entangled systems cannot be described independently, even when they are spatially separated at larger scales. Their properties are correlated in a way that ignores distance. Some physicists suspect that entanglement plays a role in the emergence of space itself. In this picture, spatial proximity reflects the degree of entanglement. Highly entangled systems appear close. Weakly entangled systems appear far apart. If this is true, then distance is not fundamental. It is a manifestation of quantum correlations. At the Planck scale, where entanglement is expected to be pervasive, the notion of distance as separation may simply not apply. This does not mean everything is everywhere at once. It means that where is not the right question. This realization shifts how we think about the Planck volume. It is not a tiny box with well-defined edges. It is a regime where the concept of edges loses clarity. When distance loses meaning, volume loses meaning too. Volume is built from distance. If you cannot define length reliably, you cannot define volume reliably. This reinforces the idea that the Planck volume is not a smallest container, but a boundary beyond which spatial concepts become approximate. It is worth pausing here to notice how this changes the emotional tone of the subject. The idea that distance loses meaning can sound alarming at first. It can feel like the universe is dissolving into something incomprehensible. But there is another way to experience it. At human scales, distance is a source of separation. Things are far away. We cannot reach them. At the smaller scales, the loss of distance suggests a kind of closeness, a deep interconnectedness where separation is not fundamental. This is not a mystical statement. It is a structural one. The universe, at its deepest level, may not be arranged as isolated points separated by space. It may be arranged as a web of relationships from which space emerges. If distance begins to dissolve near the smallest volumes, what happens to time itself when space no longer provides a stable framework? Time is so familiar that it almost disappears into the background of experience. It moves forward, it carries moments with it, it separates memory from anticipation. Even when we talk about time behaving strangely, slowing down near massive objects or stretching for fast-moving observers, we still imagine it as something that flows, something that can be measured, something that exists reliably beneath everything else. When space begins to lose its calm structure, time does not remain untouched. To understand what time might be like inside the smallest meaningful volume, we need to let go of the idea that time is a universal, steadily ticking backdrop. That idea works extraordinarily well at human scales. It even works in most astrophysical situations. But like smooth space, smooth time is an approximation, one that begins to unravel when geometry itself becomes unstable. The first step is to recognize how deeply time is tied to space in modern physics. In everyday thinking, time feels separate. Space is where things are. Time is when things happen. But in relativity, space and time are woven together into a single structure. Distances depend on motion. Durations depend on gravity. What one observer calls now may not align with another observer's now. This interdependence already hints that if space becomes uncertain, time will not remain intact. At large scales, the interweaving is gentle. Space-time behaves smoothly. You can define clocks, you can synchronize them. You can agree within reasonable limits on durations and sequences. The universe allows a shared temporal structure to emerge. As we move toward the smallest scales, that shared structure begins to fragment. Time, like distance, is not something we observe directly. We infer it from change. A clock is not a fundamental time object. It is a system that undergoes regular, predictable change. The ticking of a clock is a physical process governed by laws of motion, energy, and interaction. If the underlying geometry that supports those processes becomes unstable, the clock loses its reliability. At the Planck scale, the same issues that plague distance measurement also plague time measurement. To measure very short durations, you need high energies. High energies distort space-time. Distorted space-time alters the flow of time. Once again, measurement interferes with what it measures, but time has an additional vulnerability. Unlike distance, time is directional. We experience it as having an arrow, a before and an after. That arrow is not imposed by fundamental equations in most areas of physics. It emerges from statistical behavior, from entropy increasing, from systems moving from ordered states to disordered ones. Inside the smallest meaningful volume, the conditions that give rise to this arrow may not exist. To see why, consider what entropy requires. Entropy is defined for systems with many degrees of freedom. It relies on counting arrangements, on coarse graining, on averaging over many components. At the Planck scale, there may not be many of anything in the usual sense. The system may be too small to support a meaningful notion of entropy. If entropy loses meaning, the arrow of time loses its foundation. This does not mean that time runs backward. It means that the distinction between forward and backward may not apply. Another way to approach this is to think about time as a parameter in equations. In quantum mechanics, time is often treated as an external parameter. The system evolves in time, but time itself is not part of the quantum system. It is assumed to exist independently. In general relativity, time is part of the system. It is shaped by gravity. It flows differently depending on location and motion. When you try to combine these two frameworks, you encounter what physicists call the problem of time. In some formulations of quantum gravity, time disappears from the fundamental equations altogether. The equations describe relationships between states, not evolution in time. This is not a metaphor, it is a literal feature of the mathematics. If the fundamental description of the universe does not include time as a variable, then time must emerge in some approximate way. It cannot be fundamental. It must be something that appears when conditions allow. The smallest volumes of space are precisely the conditions where this emergence may fail. Inside such a regime, there may be no well-defined notion of before and after. There may be no global ordering of events. Instead, there may be correlations without sequence. This is extremely difficult to picture, because our minds are built to think in sequences. We remember one thing happening after another. We plan, we anticipate, we narrate. But narration itself requires time. When time loses meaning, narrative dissolves. This does not mean nothing happens. It means that happening is not organized along a single timeline. Another way to see this is through the role of clocks. Every clock relies on a periodic process, an oscillation, a decay, a vibration. These processes require stable laws and stable geometry. They require a background in which cycles can repeat reliably. At the Planck scale, geometry fluctuates too violently to support such cycles. Any would-be clock is overwhelmed by quantum fluctuations of space-time. There is no steady beat to count. Without clocks, time cannot be operationally defined. This leads to a subtle but important point. Time, like distance, may be operationally limited. Below a certain scale, there may be no physical process that can function as a clock, not because we lack ingenuity, but because the universe does not permit stable periodicity at that scale. If no clock can tick, then time cannot be measured, and if time cannot be measured, then assigning durations becomes meaningless. This does not imply that reality freezes. It implies that the language of duration does not apply. Another angle comes from considering causality. Time is deeply tied to cause and effect. Causes precede effects. Events influence later events. This ordering gives time its direction and structure. At small scales, causality itself may become subtle. In a fluctuating geometry, the light cones that define causal structure may blur. The distinction between time-like and space-like separation may become uncertain. Events may not have a definite causal order. This does not necessarily mean that causality is violated. It may mean that causality is not tied to a single timeline. Instead, it may be encoded in correlations that do not map neatly onto before and after relationships. Some approaches to fundamental physics suggest that causality, not time, is the more basic concept. In these views, the universe is a network of causal relationships. Time emerges as a way of ordering those relationships when they are sufficiently stable and layered. Inside the smallest volumes, that layering may not exist. Another important aspect of time inside the smallest volume is the role of energy-time uncertainty. Just as there is an uncertainty relation between position and momentum, there is an uncertainty relation between energy and time. Short durations imply large uncertainties in energy. At the Planck scale, these uncertainties become extreme. Energy fluctuates violently. Since energy affects geometry, geometry fluctuates violently. Since geometry affects time, time fluctuates violently. The loop closes. This feedback loop makes it impossible to isolate time as an independent variable. Any attempt to define a duration changes the energy. Any change in energy alters the geometry. Any alteration of geometry changes the meaning of duration. Time becomes relational, contextual, dependent on the state of the system. This is why some physicists say that at the deepest level, the universe may be timeless. Not in the sense that nothing changes, but in the sense that change is not parameterized by an external clock. Instead of time, the fundamental description may involve correlations between states. One configuration is related to another, but not ordered along a universal timeline. In such a description, what we call time emerges when those correlations form patterns that can be approximated as sequences. This emergence requires scale. At large scales, many subsystems interact. Entropy increases. Stable clocks can exist. The arrow of time appears. Time becomes a useful, even indispensable concept. At the smallest scales, those conditions are absent. It is worth emphasizing that this does not mean the smallest volumes are special in a mystical sense. They are special because they are too small to support the structures that make time meaningful. Just as a single molecule does not have a temperature, a Planck scale region may not have a time. Another way to approach this is to consider the idea of now. At human scales, now feels real. It feels like a shared moment. But even in relativity, now is observer-dependent. Different observers slice space-time differently. At the Planck scale, the idea of a global now becomes meaningless. There is no consistent way to define a present moment across fluctuating geometry. Instead of a present, there may be a collection of relational states, none privileged as the moment. This challenges our intuition deeply, because so much of our identity is tied to being in time. We think of ourselves as moving through time. We age, we remember, we expect. Inside the smallest volumes, those concepts do not apply. But this is not a loss, it is a clarification. Time is not something that exists everywhere, and always in the same way. It is something that emerges when conditions allow. The smallest volumes are simply too small. There is also a connection here to the idea of minimum duration, sometimes called the Planck time. Just as there is a Planck length, there is a Planck time derived from the same constants. It represents the time it takes light to travel a Planck length. Like the Planck volume, the Planck time is not necessarily the smallest possible time. It is the smallest time interval that can be meaningfully discussed within our current framework. Below that, the idea of duration loses clarity. This reinforces the parallel between space and time. Both have scales below which their usual meanings fail. Both are tied to measurement. Both rely on stable geometry. Both emerge together. Inside the smallest volume, there may be no inside in the spatial sense, and no during in the temporal sense. This does not mean the universe disappears at that scale. It means that the universe is described differently. Instead of asking how long something lasts, you ask how states relate. Instead of asking when something happens, you ask how it is correlated with something else. These are not lesser questions, they are deeper ones. As we let this idea settle, it becomes clear why discussions of the Planck volume often feel abstract. It is not because physicists enjoy abstraction. It is because our everyday concepts are stretched beyond their range. But there is also something quietly reassuring in this. The universe does not demand that we understand it in one way at all scales. It allows for different descriptions, each appropriate to its domain. Time as we experience it is real where we live. It governs our bodies, our thoughts, our sleep. It remains meaningful at every scale that matters for daily life. The fact that it loses meaning at the smallest volumes does not diminish it. It contextualizes it. Black holes enter this discussion not as exotic side characters, but as unavoidable consequences of taking gravity seriously. They are what happens when compression is pushed as far as the known laws of physics will allow. Long before we reach the smallest meaningful volume in an abstract theoretical sense, gravity gives us a concrete laboratory where space, time, and density are driven toward their limits. To understand why black holes matter so much here, it helps to strip away the dramatic imagery that usually surrounds them. Forget the swirling disks and glowing jets for a moment. At its core, a black hole is simply a region where matter and energy have been compressed so tightly that space-time itself bends inward beyond a critical threshold. Nothing mysterious is required. No exotic materials. Just gravity doing its job without interruption. Compression is the key idea. In everyday life, compression feels limited. You can squeeze a sponge only so much. You can compress air, but it pushes back. Solids resist. Even at the atomic level, electrons repel each other, nuclei resist intrusion, and forces balance out. Nature seems full of cushions and buffers. Gravity ignores those buffers. When enough mass is present, gravity overwhelms every other resistance. Electron pressure fails. Nuclear forces fail. Eventually, even the structure of space-time yields. That surrender is what creates a black hole. From the outside, a black hole looks deceptively simple. It has a mass, a charge, and a spin. Beyond that, its internal details are hidden behind an event horizon, a boundary that marks the point of no return. Once something crosses that boundary, it cannot send information back out, no matter how energetic or clever it might be. The event horizon is not a physical surface. It is a geometric boundary, defined by the curvature of space-time, but it plays a crucial role in how compression reaches its limits. As matter collapses inward, density rises. Energy is packed into smaller and smaller volumes. According to classical general relativity, this collapse continues without end, funneling everything into a singularity, a point of infinite density and zero volume. That prediction is a red flag. Physics has encountered infinities before, and they have always signaled that a theory is being pushed beyond where it applies. Infinite density is not a physical result. It is a mathematical warning. When general relativity predicts a singularity, it is telling us that smooth geometry has failed. The equations demand something impossible because the assumptions behind them no longer hold. This is where the limits of compression become inseparable from the limits of space itself. If matter could truly be compressed into a point of zero volume, then the idea of a minimum volume would be meaningless. Space would allow infinite compression. But every indication we have suggests that this is not what actually happens. Instead, the singularity is widely believed to be replaced by something else when quantum effects are taken into account. Black holes, then, become testing grounds for the idea that space cannot be compressed arbitrarily. To see why, consider the role of the Planck scale again. As matter collapses and density increases, eventually the energy density reaches a point where quantum gravitational effects can no longer be ignored. This happens well before a literal zero volume is reached. At these densities, the smooth description of spacetime breaks down. Geometry fluctuates. Volumes become uncertain. The idea of a single, well-defined point no longer applies. In other words, compression runs into the same boundary we've been circling all along. The Planck volume appears again, not as a static box, but as a scale where further compression ceases to make sense in geometric terms. One way to think about this is to imagine trying to compress a fluid that becomes increasingly resistant as it is squeezed, not because of pressure in the usual sense, but because the medium itself changes character. Space-time may behave this way. As you compress energy into smaller regions, the geometry responds more violently, eventually refusing further compression by destabilizing the very notion of smaller. This is not proven, but it is strongly suggested by how black hole physics intersects with quantum theory. Another hint comes from black hole entropy. Black holes have entropy proportional to the area of their event horizons, not their volume. This is one of the most surprising results in modern physics. It suggests that the information content of a black hole, and by extension, the maximum information that can be stored in a region of space, is limited by surface area. If information is limited, then the degrees of freedom inside cannot be infinite. Infinite compression would require infinite degrees of freedom. Black hole entropy tells us that this is not allowed. This area scaling strongly hints that space has a finite informational capacity per unit area, which in turn suggests a finite structure at the smallest scales. The Planck area and Planck volume emerge naturally in these considerations. Black holes also force us to rethink what inside means. From the outside, time slows down near the event horizon. An object falling in appears to freeze as it approaches the boundary, its clock ticking more and more slowly. From the perspective of the falling object, however, nothing special happens at the horizon. It crosses without noticing. This mismatch already shows how fragile time and distance are near extreme compression. Inside the horizon, the roles of space and time swap in strange ways. Directions that once pointed outward become temporal. Movement toward the center becomes inevitable, not because of a force pulling inward, but because the geometry is structured that way. The future lies toward the center. As compression continues inward, classical descriptions predict a singular endpoint. But again, this is where the theory overreaches. Quantum considerations suggest that before such an endpoint is reached, the internal structure of spacetime becomes dominated by fluctuations. Distances cease to be well defined. Time loses its ordering. The concept of a trajectory breaks down. In this sense, black holes may already contain regions where the smallest meaningful volumes are reached. They are not theoretical curiosities. They are real objects in the universe where compression has pushed geometry to its limits. This has led physicists to speculate that black holes might reveal the true structure of space at the Planck scale. Not directly, because the interior is hidden, but indirectly through their thermodynamics and quantum behavior. One striking example is Hawking radiation. Black holes are not completely black. They emit radiation due to quantum effects near the event horizon. This radiation carries energy away, causing the black hole to lose mass over time, Hawking radiation depends on quantum fluctuations of fields near the horizon. It links gravity, quantum mechanics, and thermodynamics in a single phenomenon. Crucially, the radiation suggests that black holes have a finite lifetime. They evaporate. As they do, their mass decreases, their horizon shrinks, and eventually they reach very small sizes. What happens then? As a black hole shrinks, its density increases. Its horizon approaches the Planck scale. At that point, the description of the black hole using smooth geometry becomes unreliable. Does it vanish completely? Does it leave behind a remnant? Does it transition into some other state of space-time? These questions are still open, but they all revolve around the idea that there is a limit to compression. If space has a minimum meaningful volume, then a black hole cannot shrink beyond a certain point without changing character. The Planck scale becomes a natural stopping place. This again suggests that space resists infinite compression, not through force, but through the breakdown of geometry. Another way black holes illuminate the limits of compression is through the information paradox. When a black hole evaporates, what happens to the information about what fell in? Classical reasoning suggests it is lost. Quantum mechanics insists it must be preserved. Resolving this paradox has led to deep insights about the structure of space-time. Many proposed solutions involve the idea that information is stored at or near the horizon, not deep inside a singular point. This reinforces the idea that volume is not where the action is. The interior may not contain arbitrarily detailed structure. Instead, the relevant degrees of freedom may be encoded in ways that do not correspond to simple spatial packing. This, again, aligns with the notion that there is a limit to how much can be compressed into a region of space. Black holes also challenge the idea that space is passive. Inside a black hole, geometry dictates fate. Paths converge, time points inward. Compression is not just something happening within space. It is something space itself enforces. This makes black holes an extreme manifestation of the restless geometry we discussed earlier. They are places where gravity does not merely curve space gently, but dominates it entirely. And yet, even in this domination, there are limits. The existence of a smallest meaningful scale implies that geometry cannot collapse into nothingness. It must transition into something else, something that smooth descriptions cannot capture. This brings us back to the idea of the Planck volume as a boundary of description. Black holes push matter and energy toward that boundary naturally. They are not engineered thought experiments. They are astrophysical facts. This gives weight to the idea that the smallest volumes are not just mathematical artifacts. They are relevant wherever gravity is extreme. It also reframes how we think about singularities. Instead of being literal points of infinite compression, they may be placeholders for a quantum gravitational regime where the notion of volume dissolves. In that regime, asking how small things get is the wrong question. The right question is how geometry reorganizes itself when further compression is no longer meaningful. Black holes, then, are not failures of physics. They are invitations. They invite us to consider that space has a structure that resists infinite compression, that geometry is not infinitely pliable, that there is a scale where space stops behaving like a container and starts behaving like a participant. When we turn our attention to the early universe, we're no longer dealing with a rare or isolated case of extreme compression. We're dealing with a moment when everything we now see, every galaxy, every particle, every stretch of space itself, was once packed into conditions so dense and energetic that the usual language of size, distance, and duration strains almost immediately. This is not speculation in the casual sense. The expansion of the universe is one of the most firmly established observations in modern science. Galaxies are moving away from one another, light from distant regions is stretched, space itself is expanding. When we mathematically reverse that expansion, running the cosmic clock backward, the universe becomes smaller, hotter, and denser. At first, this backward journey feels manageable. A few billion years ago, galaxies were closer together. Go further back and galaxies had not yet formed. matter existed as hot plasma. Go further still, and even atomic nuclei could not survive. Particles collided too violently. The universe was a dense, seething soup of energy and elementary constituents. At each step, physics still works, although the dominant forces change. Nuclear physics gives way to particle physics. Symmetries restore, forces unify, temperature rises, density increases. And then, as we keep going, we approach a boundary that feels familiar by now. Eventually the energy density becomes so high that gravity itself must be treated quantum mechanically. The smooth description of spacetime used in cosmology begins to fail. Calculations point toward a singular beginning, a point where density becomes infinite and volume shrinks to zero. Once again, this infinity is a warning, not a destination. The classical picture of the Big Bang as a literal point of zero volume is almost certainly not the true story. It is the point where our equations, built on smooth geometry, cease to apply. This is where the idea of the universe at its tightest becomes inseparable from the idea of a minimum meaningful volume. As we trace the universe back toward its earliest moments, we inevitably approach the Planck regime, not because we want to, but because the numbers force us there. Energy densities rise, length scales shrink, time intervals shorten. Eventually, the Planck scale appears as the place where the extrapolation stops being trustworthy. At this stage, the universe is not just small, it is operating under rules we do not fully know. To understand why this matters, it helps to be precise about what we mean when we say the early universe was small. In everyday terms, small means fitting inside something else. But the early universe did not exist inside a larger space. There was no external container. Space itself was what was small. That distinction is crucial. When we say the universe was compressed, we do not mean that matter was squeezed into a corner of a pre-existing room. We mean that the room itself was compressed. The distances between all points were smaller. The total spatial volume was smaller. This makes the early universe the ultimate case study for understanding how small space itself can become. As the universe approaches the Planck scale, several things happen simultaneously. The energy density becomes enormous. Quantum fluctuations of fields become significant. Gravity becomes strong at microscopic scales. Geometry becomes unstable. These effects do not happen one after another. They overlap. The universe at its tightest is not a calm, static object waiting to expand. It is a dynamic, fluctuating state where the distinction between space, time, and energy is blurred. In classical cosmology, the Big Bang is often depicted as an initial singularity, a point in time when everything began. But this depiction carries a misleading implication. It suggests a moment that exists within time, a first tick of the cosmic clock. Quantum considerations challenge this picture. If time itself loses meaning at the smaller scales, then the phrase, "the beginning of time," becomes problematic. There may not have been a first moment in the usual sense. Instead, there may have been a transition from a regime where time was not well defined to one where it emerged gradually. In this view, the universe at its tightest was not located at a specific time. It was a boundary between descriptions. This reframing helps explain why so many questions about the Big Bang lead to paradoxes. What happened before the Big Bang? What caused it? What came first? These questions assume a temporal framework that may not apply. Inside the Planck regime, causality may not be organized along a single timeline. The universe may have existed in a state where before and after were not meaningful distinctions. As space expanded and cooled, stable geometry emerged. Entropy began to increase. Time acquired an arrow. The universe entered a phase where asking about earlier and later made sense. The tightest state of the universe, then, may not have been a moment at all. Another important aspect of the early universe is how quantum fluctuations behaved at those extreme densities. Even when the universe was extraordinarily small, it was not uniform at the deepest level. Quantum mechanics guarantees fluctuations. Energy was not evenly distributed. Fields did not sit at exact values. These tiny fluctuations were stretched by cosmic expansion and eventually became the seeds of galaxies and large-scale structure. This means that the universe we see today carries imprints of its earliest, tightest state. But here is the key point. Those fluctuations were not fluctuations within a fixed background of space. They were fluctuations of space-time itself. At the Planck scale, the distinction between matter fluctuations and geometric fluctuations disappears. Density variations are inseparable from curvature variations. Geometry and content are two ways of describing the same thing. This again challenges the idea of a sharply defined minimum volume. If geometry fluctuates violently, then the size of the universe at its tightest is not a single number. It is a range, a probabilistic distribution. There may not have been a smallest volume in the sense of a fixed minimum. There may have been a smallest regime where volume lost its usual meaning. This subtlety matters because it changes how we think about the origin of the universe. If the universe began from a state with no meaningful geometry, then asking how big it was is like asking how hot a single molecule was. The question does not apply. Instead, the relevant question becomes how geometry emerged. Many modern cosmological models explore this idea. Some propose that the universe underwent a bounce, contracting to a minimum size and then expanding again. In these models, the Planck scale plays a central role as the point where contraction halts and expansion begins, not because of repulsive forces, but because geometry itself cannot be compressed further. Other models suggest that the universe emerged from a quantum state without classical spacetime, a sort of pre-geometric phase where spatial concepts were not yet applicable. In all of these scenarios, the early universe at its tightest is not described as a tiny ball of space sitting at the beginning of time. It is described as a regime where space and time are in the process of becoming. This perspective also sheds light on why the universe appears so uniform at large scales. The early universe was not smooth because it was small. It was smooth because the underlying state did not support large variations in geometry. As space expanded, small fluctuations were stretched, but large differences could not exist initially because geometry itself was not yet fully defined. This is another hint that there is a minimum meaningful structure to space. If space could be arbitrarily subdivided, then the early universe could have been arbitrarily irregular. But observations show remarkable uniformity. That uniformity suggests constraints at the smallest scales. The early universe also confronts us with the question of volume in a new way. Volume is normally defined relative to a metric, but if the metric itself fluctuates wildly, volume becomes an emergent quantity. At the tightest state, there may have been no well-defined metric at all. Instead, there may have been quantum correlations from which metric properties emerged as the universe expanded. In this view, the early universe was not small in the sense of having a tiny volume. It was small in the sense that the range of possible geometries was limited. This reframing aligns with the idea that the Planck volume is not a smallest box but a smallest regime. Another important feature of the early universe is that it was dominated by energy, not matter. Matter as we know it did not yet exist. Particles were constantly created and destroyed. Fields were excited. Forces may have been unified. This matters because energy is what curves space-time. When energy densities are extreme, geometry responds dramatically. At the tightest state, geometry was driven almost entirely by energy fluctuations. This reinforces the idea that geometry could not settle into a stable configuration. Space could not become calm until energy densities dropped below a certain threshold. Expansion was not just a stretching of space, it was a calming of geometry. As the universe expanded, energy density decreased. Quantum fluctuations became less violent. Gravity became weaker at small scales. Geometry smoothed out. Distance and time became meaningful. Volume became well-defined. This gradual emergence of calm geometry suggests that the smallest volumes are not static features of reality. They are transitional features. The early universe at its tightest was not a permanent state. It was a fleeting regime, a passage through a boundary where old descriptions gave way to new ones. This is another reason why asking for precise numbers can be misleading. How big was the universe at the Planck time? How long did that phase last? These questions assume stable quantities that may not have existed yet. What matters more is the process. The universe moved from a state where geometry was undefined or fluctuating to a state where geometry became stable enough to support distances, durations, and volumes. In this sense, the early universe teaches us that minimum volume is not about reaching a smallest container. It is about reaching a smallest condition where space as a concept comes into focus. This perspective also connects back to black holes. Both involve extreme compression. Both push geometry to its limits. Both likely involve transitions to quantum gravitational regimes where smooth spacetime breaks down. The difference is that black holes are local. The early universe was global. In black holes, a region collapses within a larger space-time. In the early universe, the entire space-time was involved. This makes the early universe the most extreme example of the universe reaching its tightest configuration. And yet, despite this extremity, the universe emerged into a state where calm geometry could exist. This suggests that the Planck regime is not a dead end. It is a gateway. Once we reach the idea of a smallest meaningful volume, a question naturally lingers, even if we try not to ask it too sharply. If the Planck volume marks a boundary where space, distance, and time lose their usual meanings, does that boundary represent the absolute smallest thing that can exist? Or is it only the smallest thing that can be described using the tools we currently have? This distinction is subtle, but it matters more than it first appears. When people ask whether anything can exist smaller than the Planck volume, they are often imagining objects, tiny particles, little fragments of space, something that occupies a region, but a region even smaller than the one we've identified as minimal. That intuition comes from a long habit of thinking in terms of objects inside containers. We imagine size as something that belongs to things. At the smallest scales, that habit becomes unreliable. The first thing to clarify is what we mean by exist. At everyday scales, existence is tied to location. Something exists because it is somewhere. You can point to it. You can say where it is and when it is. But as we have been uncovering, location itself is a concept that may not survive below a certain scale. If space loses meaning, then existence can no longer be defined as occupying a region of space. That alone reshapes the question. If something cannot be said to occupy a region, then asking how big that region is becomes the wrong approach. The Planck volume may not be the smallest container. It may be the smallest context in which containers make sense at all. So can anything exist smaller than this? If we mean, can anything occupy a smaller spatial volume, the most careful answer is that the question may not apply. Below the Planck scale, the concept of spatial volume may no longer correspond to anything physically definable. There is no smaller box to put something in, because boxes are part of the geometric language that has broken down. This does not mean that reality stops. It means that existence takes on a different form. One helpful way to approach this is to think about how physics has treated other limits in the past. Consider the idea of temperature again. There is a lowest possible temperature, absolute zero. But asking whether something can be colder than absolute zero misunderstands what temperature measures. Temperature describes the average kinetic energy of many particles. Below a certain point, the concept ceases to apply. It is not that colder states exist but are forbidden. It is that colder no longer has meaning. The Planck volume may function in a similar way for space. Below it, smaller may not be a meaningful descriptor. Another analogy comes from frequency. There is a highest frequency of light that can be meaningfully discussed in certain physical contexts, because beyond that, the energy involved changes the system qualitatively. Asking for higher frequency may lead to particle creation, gravitational effects, or breakdowns in description. The parameter loses its clean interpretation, Space may behave the same way. Size is not an unlimited dial you can keep turning. That said, physicists do not generally assume that nothing exists beyond the Planck scale. Instead, they suspect that something does, but that it is not spatial in the way we're used to. This leads to a crucial shift in perspective. The Planck volume may not be a smallest thing. It may be a smallest translation layer. Above it, reality can be translated into geometry. Below it, geometry is no longer the correct language. So what might exist below? Many approaches to fundamental physics suggest that the deepest level of reality is not made of spatial objects at all. Instead, it may be made of relationships, states, or informational structures that do not have size in the geometric sense. In these views, space is emergent. It is not the stage, it is the outcome. If space emerges, then asking whether something exists inside a smaller space becomes like asking whether a thought exists inside a smaller distance. The categories don't align. This reframing helps resolve a lot of confusion. It allows us to say that yes, something may exist below the Planck scale, but not as something smaller than space. Rather, it exists prior to space. That word, prior, must be used carefully. It does not mean earlier in time. Time too may not exist at that level. It means logically prior, structurally prior. Another way to approach this is to think about degrees of freedom. Physics often describes systems in terms of degrees of freedom, the independent ways a system can vary. In a region of space, there are only so many degrees of freedom available. Black hole entropy suggests that this number is finite and scales with area. If the degrees of freedom are finite, then you cannot pack arbitrarily many independent entities into a region, no matter how much you try to subdivide it. Beyond a certain point, additional subdivisions do not add new physical possibilities. This implies that even if there is something below the Planck scale, it does not correspond to additional independent spatial structure. In other words, you cannot gain new physics simply by carving space into smaller and smaller pieces. This again suggests that the Planck volume is not a smallest object, but a smallest capacity. Another important angle comes from the role of measurement. Physics defines existence operationally. Something exists in a physical sense if it can, at least in principle, influence other things in a measurable way. Below the Planck scale, measurement becomes impossible in the usual sense. Any attempt to probe smaller regions creates gravitational effects that erase the distinction you're trying to make. If no measurement can distinguish between two configurations, then physics treats them as the same. That does not mean there is literally nothing there. It means there is no physical difference. So when we ask whether something exists smaller than the Planck volume, we must ask whether that existence would have any observable consequence. If it does not, then physics has no reason to treat it as distinct. This is not a limitation of curiosity. It is a boundary of empirical meaning. Another reason physicists are cautious about declaring the Planck volume an absolute smallest thing is that history has taught them humility. Many limits once thought fundamental turned out to be approximations. Classical physics thought time was absolute. It wasn't. Classical physics thought space was rigid. It wasn't. Classical physics thought matter was continuous. It wasn't. So it is entirely possible that the Planck scale is not the final word. But if it is not, whatever lies beyond it will not look like smaller space. That is the key point. Any theory that meaningfully goes beyond the Planck scale must abandon the idea that reality is fundamentally spatial. It must describe something deeper, something from which space itself emerges. Several modern approaches attempt this in different ways. Some suggest that the fundamental ingredients are quantum states defined on abstract mathematical structures, with no spatial interpretation until large numbers of them interact. Others suggest that information itself is the basic currency, and that space arises as a way of organizing information. Others propose algebraic or combinatorial structures, where adjacency, not distance, is fundamental. In all of these cases, asking whether something is smaller than the Planck volume is like asking whether a letter in a book is smaller than the meaning of a word. The question mixes levels of description. Another subtlety is that the Planck volume is defined using constants that come from our current understanding of physics. If those constants are emergent themselves, then the Planck scale may be emergent too. This does not weaken its importance, it reframes it. The Planck volume may be the smallest scale at which spacetime behaves classically enough to be described geometrically. Below it, spacetime is replaced by something else. That something else may not have size, shape, or duration. It may not be meaningful to say that it is small at all. This helps explain why attempts to imagine sub-Planckian objects often run into paradoxes. We try to picture something occupying a region smaller than the smallest region, which is like trying to draw a shape using colours that do not exist. The universe is not forbidding us from imagining. It is telling us that imagination must change its language. There is also an important psychological aspect to this question. Humans are naturally inclined to search for smallest things. It gives a sense of closure, a bottom, a final layer. We like to believe that if we dig far enough we will reach something solid. The Planck volume resists that narrative. It suggests that the universe may not be built from a stack of smaller and smaller objects. Instead, it may be built from layers of description, each valid in its domain. At one layer, geometry works. At another, it does not. That does not mean the deeper layer is less real. It means it is real in a different way. So can anything exist smaller than the Planck volume? If by exist we mean have a spatial size smaller than that, the best answer is that the question likely does not apply. If by exist we mean be part of the fundamental structure of reality, then almost certainly yes. But that existence will not be spatial existence. This conclusion can feel anticlimactic if we are hoping for a smallest dot, a final grain of space. But it is actually quite powerful. It tells us that the universe is not a hierarchy of smaller containers, but a hierarchy of concepts. Space is one of those concepts. It works beautifully at the scales we inhabit. It works astonishingly well across cosmic distances. It even works surprisingly well down to the scales of particles. But it does not work everywhere. The Planck volume marks the place where space itself stops being the right idea. And once we accept that, the question shifts. Instead of asking what is smaller than the Planck volume, we ask what kind of structure gives rise to space in the first place. That question does not lead to smaller things, it leads to different ones. When we reach the Planck volume in our thinking, we often pause instinctively, as if we've arrived at a physical object, a boundary, a smallest cell, something that exists in the same sense that atoms, particles, or even black holes exist. But this instinct comes from habit more than from evidence. We're used to limits being things. We're used to walls, edges, and final pieces. The Planck volume does not behave like that. To understand whether it is a physical thing or a mathematical warning, we need to examine how physics has encountered limits before, how mathematics communicates trouble, and why the Planck scale keeps appearing, even when approached from very different directions. Let's start with how physics normally treats physical things. A physical thing can, at least in principle, be interacted with. It can influence other things. It can be detected, even indirectly. An electron is not seen directly, but its effects are measured. A black hole cannot be touched, but its gravity shapes stars and light. Even dark matter, elusive as it is, earns its status as physical because it leaves fingerprints on galactic motion. A mathematical warning, by contrast, does not act. It signals. It tells you that the rules you're using are no longer valid in the regime you're pushing into. In physics, warnings often appear as infinities. When equations produce infinite values, physicists do not celebrate the discovery of infinite quantities. They take it as a sign that the theory is being applied where it should not be. Infinite energy densities, infinite curvatures, infinite probabilities are not features of reality. They are symptoms of a mismatch between description and domain. The Planck volume appears precisely at such a mismatch. It shows up at the point where smooth geometry, quantum uncertainty and gravity collide in a way that makes the equations misbehave. It marks the place where continuing to use familiar mathematical tools leads to contradictions. That alone suggests caution. If the Planck volume were a physical thing, we might expect it to appear as a discrete unit in experiments, or as a feature with observable consequences at accessible scales. So far, it has not. Its role is indirect. It constrains what theories can say without breaking. This is a strong hint that the Planck volume functions primarily as a warning sign. But the story is not that simple. The Planck scale is not an arbitrary number. It is not chosen to fix a problem artificially. It emerges inevitably when you combine fundamental constants that describe real, measurable aspects of the universe. The speed of light governs causality and relativity. Planck's constant governs quantum uncertainty. The gravitational constant governs how energy curves space-time. These constants are not bookkeeping devices. They are physical. When you combine them, the resulting scale inherits that physical grounding. The Planck volume is not just a number on paper. It reflects a real interplay between physical principles. This is where the ambiguity arises. The Planck volume behaves like a warning, but it is a warning rooted in physical structure. It is not a random artifact of mathematics. It is the place where multiple, independently successful descriptions of nature stop agreeing. That makes it different from a purely mathematical pathology. To see this more clearly, consider a simpler example. Classical mechanics predicts that a charged particle orbiting a nucleus should radiate energy continuously and spiral inward, collapsing the atom. This prediction is mathematically consistent within classical electrodynamics, but it is physically wrong. The warning sign was not an infinity, it was instability. The resolution was not to declare atoms impossible. It was to realize that classical mechanics was being applied beyond its range. Quantum mechanics replaced it. The Planck volume may play a similar role. It may not be telling us that space is made of Planck-sized chunks. It may be telling us that treating space as smooth and continuous beyond a certain scale is no longer valid. In this sense, the Planck volume is like the Bohr radius was before quantum mechanics. It appeared as a characteristic scale where classical ideas failed, pointing toward a deeper description. Another way to evaluate whether the Planck volume is a physical thing is to ask whether it behaves like one in theoretical frameworks that attempt to go beyond our current theories. In some approaches to quantum gravity, volumes are indeed quantized. Regions of space have discrete volume eigenvalues. In those frameworks, the Planck volume plays a role similar to the smallest non-zero unit of volume. However, even in these theories, the Planck volume is not a rigid cube floating in space. It is a value that arises from the spectrum of an operator. It is relational and context-dependent. It does not sit at a location. It does not exist independently of the quantum state of geometry. This already distinguishes it from ordinary physical objects. In other approaches, the Planck volume does not appear as a discrete unit at all. Instead, it marks the scale where fluctuations become uncontrollable and classical geometry dissolves. Below it, volume is not quantized, but undefined. The fact that very different theoretical frameworks all take the Planck scale seriously, while disagreeing on whether space is discrete, suggests that the Planck volume is more fundamental as a boundary than as a building block. It is a point of convergence, not a component. Another important clue comes from how the Planck volume behaves under changes of description. Physical things persist across descriptions. An electron remains an electron whether you describe it with wave functions, field operators, or scattering amplitudes. The Planck volume, by contrast, changes its interpretation depending on the framework. In one theory, it is a minimum unit. In another, it is a cutoff. In another, it is a scale of transition. This flexibility is characteristic of warning signs. Consider the speed of sound in a material. It is not a fundamental limit of nature, it is a limit of a description. Below that speed, sound waves propagate cleanly. Above it, shocks form and the equations change character. The speed of sound is physically meaningful, but it is not a fundamental constant of the universe. It marks the boundary of a regime. The Planck volume may be analogous, but at a far deeper level. It marks the boundary of geometric description. Another way to approach this question is to ask whether the Planck volume can be isolated. Can you take a region of space and say, this region has exactly one Planck volume? Operationally, the answer appears to be no. Any attempt to isolate such a region requires energies that disrupt the geometry. You cannot prepare a system with a well-defined Planck scale volume without invoking quantum gravitational effects that destroy the very definition of volume. This inability to isolate is telling. Physical things can, in principle, be prepared and manipulated even if it is difficult. Warning signs cannot. They appear only when you try to go too far. Another angle is to look at how the Planck volume behaves under scaling. If you imagine zooming in on space, classical geometry allows you to keep zooming indefinitely. The Planck volume interrupts that zoom. But it does not appear as a feature you zoom into. It appears as a failure of zooming itself. This is an important distinction. If the Planck volume were a physical thing, zooming in would eventually reveal it. If it is a warning, zooming in reveals nothing new, and instead breaks the rules of the zoom. That is exactly what happens. As you attempt to probe smaller regions, you do not encounter a smallest cube. You encounter black holes, quantum fluctuations, and undefined geometry. The Planck volume is not encountered. It is enforced. This enforcement is not arbitrary. It arises from the interplay of gravity and quantum mechanics. But its role is to stop you from continuing with the same conceptual tools. That is the hallmark of a warning. However, calling it just a warning risks understating its importance. The Planck volume is a warning written into the fabric of the universe. It is not a red sign placed by humans. It is encoded in the way energy, space, and uncertainty interact. In that sense, it is as real as any physical constant. It tells us something deep about the structure of reality. It tells us that space is not infinitely divisible in any operationally meaningful way. It tells us that geometry is not fundamental all the way down. It tells us that measurement has limits that cannot be bypassed by clever engineering. These are physical statements, so perhaps the most accurate answer is that the Planck volume is not a physical thing, but it is a physical warning. It is not an object, but it is not arbitrary either. It is a boundary imposed by nature itself, not by human ignorance. This distinction becomes clearer when we consider how physics progresses. New theories do not erase old ones. They explain why the old ones worked where they did and failed where they didn't. Quantum mechanics did not erase classical mechanics. It explained why classical mechanics works at large scales and fails at small ones. Relativity did not erase Newtonian gravity. It explained why Newtonian gravity works at low speeds and weak fields. A successful theory of quantum gravity will not erase space. It will explain why space behaves smoothly at large scales and breaks down at small ones. In that future theory, the Planck volume will likely appear as a derived scale, a place where one description gives way to another. It will not appear as a smallest brick of space unless that is required by the deeper structure. And even if it does, its meaning will be relational, not object-like. Another important aspect of the Planck volume as a warning is that it forces humility. It reminds us that even our most successful theories have domains. It discourages the assumption that we can simply extrapolate familiar ideas indefinitely. This humility is productive. It opens the door to new concepts. If the Planck volume were simply a physical thing, the story might end there. Space would have a smallest unit. Done. But because it behaves like a warning, the story continues. It demands explanation. Why does geometry fail here? What replaces it? How does space emerge from whatever lies beneath? These questions are not about smaller things, they are about different structures. This shift in questioning is perhaps the most important consequence of recognizing the Planck volume as a warning rather than an object. It redirects curiosity away from ever finer subdivision and toward emergence. And emergence is where many of the most promising ideas now live. The Planck volume also serves as a unifying signpost. It appears in black hole physics, cosmology, quantum field theory, and information theory. These are very different domains, developed with different motivations. The fact that they all stumble at the same scale is unlikely to be coincidence. Coincidences in physics tend to disappear under scrutiny. Persistent convergence suggests underlying structure. The Planck volume, as a warning, is telling us that the universe has a built-in checkpoint. It says, beyond this point you must change how you think. That is not a limitation, it is guidance. As we step back from the details, something quietly reassuring emerges. The universe is not hiding a smallest object from us. It is protecting coherence. It is ensuring that descriptions do not overreach. Space is real where space is meaningful. Time is real where time is meaningful. Volume is real where volume can be defined. Beyond that, reality does not vanish. It reorganizes. Understanding this allows us to approach the final stretch of our exploration with a different mindset. Instead of trying to force space into ever smaller containers, we can ask how our large-scale, comfortable world emerges from something deeper. We can ask what it feels like, conceptually, to approach the edge of knowing without expecting a final piece to grab onto. And that brings us naturally to a more reflective question. If the Planck volume is not a thing but a boundary, what does it say about our place as observers? What does it feel like to stand at the edge where concepts stop working? Not because reality ends, but because our language does. There comes a point in any careful exploration where pushing further does not bring sharper detail, but a different kind of clarity. Not the clarity of answers, measurements, or definitions, but the clarity of understanding where those tools stop applying. This is the edge we've been circling, not an edge in space, not an edge in time, but an edge in description. Standing at that edge feels different from reaching a conclusion. Usually, learning ends with something solid, a law, a mechanism, a smallest piece. But here, what emerges instead is a recognition of limits that are not imposed by ignorance or missing data, but by the structure of reality itself. The Planck volume, and everything it represents, brings us to a place where the universe does not offer finer detail in the way we expect. Instead, it offers restraint. What does that feel like, conceptually? It feels unfamiliar because most of human understanding is built on reduction. We take things apart, we divide, we isolate, we zoom in. This strategy has worked astonishingly well for centuries. Chemistry reduced to atoms, atoms reduced to particles, particles reduced to fields. Each step brought deeper understanding. The edge of knowing is where that strategy pauses, not because there is nothing left, but because further division no longer produces meaningful categories. This is difficult to accept at first, because it can feel like failure. We are conditioned to think that unanswered questions mean incomplete knowledge. But there is a difference between not knowing yet and knowing that a question itself no longer fits. At the Planck scale, reality is not hiding finer structure behind a curtain. It is telling us that the curtain belongs to the stage we're trying to leave behind. One way to sense this shift is to notice how language begins to strain. Words like where, when, inside, outside, before, and after start losing their anchors. They depend on space and time being stable and separable. When those foundations loosen, the words hover without landing. This can feel unsettling, but it can also feel oddly quiet. At the edge of knowing, the universe does not feel chaotic. It feels indifferent to our categories. Geometry does not break in a violent way. It simply stops being the right lens. There is a parallel here to moments in human experience where familiar structures fall away. Deep sleep, sensory deprivation, certain moments of intense focus. In those states, the usual markers of time and space soften. Not because reality disappears, but because the mind stops organising experience the way it normally does. The Planck regime is not consciousness, and this is not a metaphor about awareness. But the structural similarity is instructive. Just as subjective time depends on neural processes, physical time depends on stable geometry. When those supports weaken, the experience changes. What reality feels like at the edge of knowing is not emptiness. It is density without structure. There is activity but no clear separation of events. There is relationship but no clear distance. There is change but no clear timeline. From the perspective of physics, this means that the most fundamental description of reality may not involve things happening somewhere at some time. It may involve correlations between states, constraints, and possibilities that only become spatial and temporal when viewed from far enough away. This perspective reframes the idea of fundamental. Fundamental does not mean smallest in size. It means least dependent on other concepts. Space depends on geometry. Geometry depends on stability. Stability depends on scale. Below a certain scale, those dependencies unravel. At the edge of knowing, physics becomes less about objects and more about consistency. What patterns can exist without contradiction? What structures can support the emergence of familiar concepts? What rules allow calm geometry to arise from restless foundations? This is why modern theoretical physics often feels abstract. It is not trying to describe what something looks like. It is trying to describe what something must be like in order for the universe we observe to exist at all. That kind of reasoning feels different from everyday explanation. It is quieter, less visual, more structural. There is also a subtle emotional shift that comes with recognizing this edge. Curiosity changes character. Instead of leaning forward aggressively trying to extract more detail, it settles back slightly. It becomes patient. At the edge of knowing, certainty gives way to coherence. This does not mean anything goes. Quite the opposite. The constraints become tighter. Any viable description of reality at this level must reproduce everything we already know at larger scales. It must explain why space feels smooth, why time flows, why distances make sense, why causality holds. The edge of knowing is not freedom from rules. It is the place where rules must be chosen carefully. Another way to describe this feeling is to think about resolution. When you increase resolution on an image past what the data supports, you don't get more detail, you get noise. At some point, the honest thing to do is stop zooming and acknowledge the limit. Physics is doing something similar here, but with integrity built in. The Planck scale is where the universe itself enforces the stop. That enforcement is not hostile, it is protective. It protects consistency. It protects causality at larger scales. It protects the emergence of time and space as usable concepts. If space were infinitely divisible and geometry infinitely precise, the universe would likely be unstable. Infinities would dominate. Small fluctuations would explode. Calm structures like atoms, stars, and living systems might never form. The edge of knowing, then, is not a flaw. It is a feature. It is the reason the universe can have layers. There is also something quietly human about this realization. We often assume that deeper understanding must feel more concrete, more mechanical. But here, deeper understanding feels more relational. Instead of asking, what is the smallest thing, we ask, what must be true for things to appear at all? This shift mirrors a broader movement in science, from substance to structure, from objects to relationships, from parts to patterns. At the edge of knowing, reality feels less like a pile of components and more like a self-consistent system. This has implications for how we think about existence itself. If existence is not tied to location at the deepest level, then being does not require occupying space. If time is not fundamental, then change does not require a ticking clock. If distance is emergent, then separation is not absolute. These ideas can sound destabilizing, but they are also unifying. They suggest that the universe is not fragmented at its base. It is connected in ways that only appear fragmented at higher levels of description. At the Planck scale, the universe does not look like a collection of tiny rooms. It looks like a dense web of constraints and possibilities. This is why attempts to imagine that scale visually often fail. Visualization relies on spatial intuition. The edge of knowing is precisely where spatial intuition no longer applies. But understanding does not require visualization. Understanding requires coherence. One of the most interesting aspects of this edge is that it is encountered independently in many areas of physics: black holes, early cosmology, quantum gravity, information theory. Each approaches from a different direction, with different motivations, and yet each arrives at the same kind of boundary. That convergence gives the edge a kind of solidity, even though it is not a thing. It is not a mystery waiting to be solved by a clever experiment alone. It is a structural feature of the universe. This does not mean experiments are irrelevant. Far from it. Experiments guide which theories are viable. They constrain possibilities. They eliminate contradictions. But no experiment will show us what lies inside the Planck volume, because inside is not the right word. The edge of knowing is not crossed by sharper tools. It is crossed by deeper frameworks, and those frameworks will not replace space and time. They will explain them. There is a quiet humility in this realization, but also a quiet confidence. Physics is not stuck. It is doing what it has always done when it reaches a boundary. It pauses, reorganizes, and moves forward with new concepts. For now, the edge remains. Standing here does not mean abandoning curiosity. It means refining it. It means learning to ask questions that fit the structure of reality rather than forcing reality into familiar shapes. This is not a cold, abstract stance. It is a deeply respectful one. It acknowledges that the universe does not owe us answers in our preferred language. It offers answers in the language that works, and perhaps most importantly, it reminds us that the calm world we inhabit, with its stable distances, steady clocks, and reliable geometry, is not trivial. It is an emergent achievement of the universe. The edge of knowing makes the ordinary feel earned. Because even though the edge exists, we do not live there. We live far above it, in a universe where space stretches comfortably, time flows gently, and understanding, while incomplete, is sufficient for wonder. After spending so much time easing downward through the foundations of space and time, it can feel almost strange to come back up again. Not abruptly, not with a snap of attention, but slowly, the way awareness returns after deep thought or quiet rest. The ideas don't disappear, they don't need to. They simply stop pressing so close to the edge and begin to settle into a scale where they can coexist with ordinary experience. This return is not a retreat. It is an adjustment. Human thought is not built to live permanently at the Planck scale. It cannot, because the Planck scale is not a place where thought has footing. There are no distances to hold on to, no durations to count, no objects to anchor attention. Remaining there would feel like trying to stand on a surface that never stops shifting. And yet, something changes after visiting that edge. When we drift back toward the scale of rooms, streets, planets, and stars, those familiar structures feel subtly different. Not because they are less real, but because their stability now feels earned rather than assumed. At human scales, space behaves itself. Distances add up. Surfaces remain where they are. You can place an object on a table and trust that it will stay there. Time ticks forward in a way that allows memory, anticipation, routine. None of this is trivial. It is the result of the universe operating far from its deepest limits. That realization carries a quiet comfort. The world you inhabit does not sit precariously on the edge of breakdown. It exists in a regime where fluctuations average out, where geometry is calm, where cause and effect line up reliably. The strange behaviours of quantum foam and restless geometry do not intrude here. They are present in a distant, indirect way, but they do not disturb daily life. This separation of scales is one of the universe's most generous features. If Planck scale behaviour leaked freely into everyday experience, nothing would hold together. Atoms would not remain stable. Structures would not persist. The fact that reality organises itself into layers, each with its own rules, is what allows complexity to exist at all. As we return to this layered view, the idea of a minimum volume takes on a different tone. It is no longer a threat to understanding, no longer an unsettling abyss beneath thought. It becomes a boundary that quietly supports everything above it. Like the deep ocean floor supports the surface without ever being seen, the Planck scale supports the calm geometry we live within without intruding into it. This perspective also reframes how we think about scale itself. Smaller is not always more fundamental in a practical sense. Deeper does not always mean more relevant to experience. The universe is not a hierarchy where only the lowest layer matters. Each layer has its own completeness. Human-scale reality is not an illusion just because it emerges from deeper structures. It is as real as any other regime, governed by rules that are stable, predictive, and meaningful. This is an important point to linger on. Sometimes discussions of fundamental physics create the impression that everyday reality is somehow provisional, flimsy, or secondary. But emergence does not imply weakness. A river emerges from molecules, but it still carves landscapes. Weather emerges from particles, but it still shapes lives. Consciousness emerges from neurons, but it still feels immediate and decisive. Space and time as we experience them emerge from deeper principles, but that does not make them less real. It makes them appropriately real for the scale at which we exist. As we drift back to that scale, the questions we ask naturally change. Instead of asking how small space can get, we ask how space behaves where it is smooth. Instead of asking whether time exists at the deepest level, we ask how time organises experience. Instead of asking what lies beyond the Planck volume, we ask how the universe maintains coherence across so many orders of magnitude. These questions are not lesser. They are grounded. They also reconnect physics to something deeply human. We are creatures who live at a particular scale. Our bodies, our senses, our memories and our thoughts all operate within a narrow band of sizes, energies and durations. Physics, at its best, does not try to pull us out of that band. It helps us understand why that band is possible. The journey down to the smallest volumes sharpens that understanding. It reveals that the calmness of our world is not accidental. It is protected by limits. Those limits are not walls, they are cushions. The Planck scale cushions the universe from infinite instability. It prevents runaway behaviour. It ensures that geometry cannot fragment endlessly. It keeps the deepest fluctuations contained, allowing higher-level order to flourish. Seen this way, the smallest meaningful volume is not an ending, it is a stabilizer. As thought returns to comfortable sizes, it becomes easier to appreciate the remarkable balance the universe maintains. At one extreme, geometry is restless, probabilistic, and undefined. At another, geometry is smooth, reliable, and predictable. Both are real, both are necessary. The universe does not choose one over the other, it layers them. This layering also explains why science feels different at different depths. At large scales, explanation feels narrative. Causes lead to effects. Systems evolve over time. At small scales, explanation becomes structural. Constraints replace stories. Possibilities replace trajectories. Neither mode is superior. They serve different domains. Human thought thrives in the narrative mode. We understand sequences, processes, and relationships unfolding over time. This is not a limitation. It is an adaptation to the scale we inhabit. Drifting back into that mode does not mean forgetting what lies beneath. It means integrating it quietly. You do not need to think about quantum foam when you walk across a room, but knowing that space remains smooth at that scale, because deeper fluctuations are averaged out, can add a subtle appreciation to the act. You do not need to think about the Planck time when you watch a sunset, but knowing that time flows reliably here because it has emerged from more fundamental correlations can make that flow feel less mechanical and more precious. The deepest insights of physics do not demand constant attention. They inform quietly. This is perhaps one of the most important lessons to carry back from the edge of knowing. Understanding does not require constant confrontation with the deepest mysteries. It requires knowing where those mysteries live and where they do not. They live far below the scale of breath, heartbeat, and thought. Here, where you are now, the universe is generous. It allows concepts to work. It allows language to function. It allows memory and anticipation. It allows rest, and rest matters. Even curiosity needs a place to settle. As we let the ideas soften and spread out again, it becomes clear that the journey we've taken is not linear. We did not move from ignorance to knowledge in a straight line. We move from familiarity to unfamiliarity and back again, carrying something subtle with us. What we carry is not a final answer about the smallest volume. It is a changed relationship to limits. Limits are no longer barriers to understanding. They are features that make understanding possible. The fact that space cannot be divided indefinitely is what allows space to be stable. The fact that time does not exist everywhere in the same way is what allows time to flow meaningfully where it does. The fact that measurement breaks down at extreme scales is what allows measurement to be reliable at human ones. This inversion is easy to miss if we rush. Drifting back slowly lets it land. The universe is not built like a machine with infinitely small gears. It is built like a layered system, where each level supports the next by not intruding into it. The deepest level does not leak noise upward. It provides structure without demanding attention. This is why you can lie still and feel the floor beneath you without worrying about quantum geometry. The floor exists because geometry is calm here. Geometry is calm here because the deepest fluctuations are constrained. Everything fits together quietly. As attention settles fully back into human scale, the questions that remain are gentler. How does the universe maintain this balance? How does calm emerge from restlessness? How does meaning arise from structure? These questions do not need immediate answers. They can sit comfortably alongside experience, and perhaps that is the final shift. After travelling through the smallest imaginable scales, the most natural response is not urgency but patience. Patience with unanswered questions, patience with incomplete theories. Patience with the idea that understanding unfolds in layers, not leaps. The universe does not reveal itself all at once. It reveals itself at the pace each scale allows. Here, at the scale of human thought, that pace is slow enough to breathe with, so the exploration does not end. It simply returns to a size where it can rest, carrying the quiet knowledge that beneath the calm surface of space and time lies a depth that supports it without disturbing it. And in that knowledge, there is no pressure to go further right now. There is only the steady presence of a universe that holds together, from the smallest meaningful limits to the comfortable spaces we inhabit, without asking us to choose between wonder and rest.